questions for Dr. Adams. I'm sure he's So can you take your seats now, please? So I thought that last session was absolutely awesome, and I think that this session's going to be even better. Our first speaker this afternoon is Dr. Lubin, who's going to be talking about beamed relativistic propulsion. So I'll just give you the microphone so everyone can hear you. Okay, thank you.
Thank you. Okay, so what I'm going to talk about is a side application of what we initially started on, which was planetary defense, which grew out of another application which has to do with other programmatic issues. I'll leave it at that. So the system we came up with is called DE-STAR, for Directed Energy System for Targeting of Asteroids. As I'll show you in a moment, it's quite a potent system, and we're keeping it on the real axis here rather than the imaginary axis, and I'll try to convince you why that's the case. So some of these quotes are interesting for people that like to see the current media coverage on planetary defense issues. Okay, we actually started the study a couple years ago. It came out of another domestic terrestrial threat issue. We released a white paper to NASA on February 14th. I woke up the next morning, it was February 15th, and the asteroid had hit Russia. So bottom line is, don't release white papers because you're going to pay for it. Al Jazeera called, amongst others. I'm going to go through this very quickly, and then I'll get to the beamed propulsion part. So we've had about 35,000 noted impacts over the last 4,000 years, and we get about 100 tons per day in hits. Most of them come in the form of relatively small space debris, so we don't worry about it so much. Different space debris than what I'll talk about in a moment. Notice that all the asteroids hit on land masses, which is very convenient, so there's a good targeting system. Not true, just where we find them. Okay, so as an offshoot of another program that I won't discuss, we came up with a system that we scaled up from that other system, and with the goal of could we deal with planetary threats. And we found that we could. So what we settled on was a standoff directed energy system using a series of phased array lasers, and I'll talk to you about that in a moment with the technical details. And there's no power source on board except photovoltaics, which is actually all you need, and I'll show you why. The baseline is to use ytterbium, which turns out to be incredibly efficient. And again, this is real, not imaginary. We're now able to phase lock lasers on large scales. The coherence length is long enough, and we can actually form beams over quite large distances. Baseline is currently 1064 nanometers. Out of a DARPA program, currently we have about 35% wall plug efficiency, conversion of electrical to photons, which is amazing if you know anything about photonics. But if you know anything about photonics, like you go into Home Depot and you want an LED light bulb, what's the efficiency of the LED light bulb? It's about 40%. This number is driven by that revolution. Aerial density is about 1 kilowatt per square meter. So people sometimes ask me, including very, very intelligent people, how are you going to get rid of the heat that you need in such a system? And the answer is it's trivial, because it's less than your body. Your body emits about 500 watts per square meter. We emit about 700 watts, so not less, but it's comparable. This is a multitasking system, of which one task can be used to propel spacecraft. Also useful for LiDAR and composition analysis and a number of other things, including space power systems. Okay, what enables this now? This would have been science fiction 10 years ago, completely science fiction. I wouldn't have come to such a conference because I'm not interested in science fiction. Yeah, I like watching science fiction like you do, but I do stuff for a living that requires me to do science fact, not science fiction. So what drives us now is, in fact, the revolution in photonics, brought on by the telecom and consumer-driven industry, soon to be driven by computer games, no doubt. We can very efficiently convert light into electricity through photovoltaics. We've known how to do that for a long time. We can also convert electricity back into light very efficiently. And we can phase lock it, which is key. We're nearing 50% efficiency, and this number is surely going to rise. It's already on a trajectory that's pushing 70% in the laboratory. Okay, so this laser pointer is an example of the photonics revolution. Right, that light bulb is also here. There's your photonics revolution. Okay, phase lock these lasers together, and you are vaporized. Okay, so coherence is key. If you don't know what coherence is, ask me later. And phase locking is key in order to get high flux to large distances. Space photovoltaics is now close to 50%. This was introduced at the end of May. It's close to 50% efficient. That's going higher. So the basic idea is very simple. You take light and you redirect it in the form of coherent, high-intensity focused light, and you heat the asteroid to the point of vaporization. It's not like Star Wars where you push the button and it goes boom. Basically, it's like materials processing where you push the button and slowly heat something up and evaporates. You start when the asteroids are far away, not when it's too late and you say duck and cover. You start when they're 1 AU away. So 1 astronomical unit, which is the distance from here to the sun on average, about the distance from here to Mars also. Okay, so what we did was we decided what size asteroid we wanted to evaporate. We took an extraordinarily conservative approach. We said we want to evaporate a 500-meter diameter asteroid completely to the molecular level in 1 year. Extraordinarily conservative. Right? In order to do so, you need about 70 gigawatts of photons if your goal is to do that. So let me go with this number for the moment, and then we'll back off in a bit. You need a spot size small enough to start evaporation, which means you need roughly 5 megawatts per square meter or larger, and I'll discuss this number. So you end up with a system which is between 1 and 10 kilometers in size. Space station's 100 meters in size. 1 kilometer is larger than we've built, but it's not impossible to build. And I'll talk to you about some of the practicalities of that. Okay, we do use fusion power. So we have a fusion generator on board just so we tether it quite far away, i.e. at 1 AU away. And so we use the sun. Right? Works very well. Phased arrays are what are key. They allow a very fine beam steering, and also we can engage multiple targets simultaneously. So we can propel a spacecraft, analyze an asteroid, vaporize another one, send power to wherever we want. Spot size is about 30 meters in diameter at 1 AU. Okay, so it's about the size of this room. So imagine this whole room at 3,000 Kelvin. Be an interesting experience. And you can imagine other uses for it. Okay, so this is extremely conservative, and I'll show you that smaller systems work. Why do you want to doubly convert? You have photons from the sun. I get this question all the time. Why don't you just take light from the sun and shine it on the asteroid? All the time. All the time. I mean, even professors ask me the same question. And the problem is phase-space conservation. The sun is not a point source. If the sun were a point source, it would work. The sun's not a point source. The sun's half degree in the sky. And the flux goes like the inverse square of the F number. It doesn't work. You can't do it. 2 days after our white paper to NASA, Dick Arwin calls me from the White House and says, I've been tasked with seeing if you're completely full of shit or not. Oops, sorry about that. I take that back on YouTube, sorry about that. Okay, anyway, Dick, don't quote me. So no, we're not. Actually, it's quite, I'll show it's quite possible to do such a thing. So if you wanted to reflect sunlight directly, you'd have to have an optical system 1 AU in diameter that is on the imaginary axis completely. It's 89.9999 degrees. Okay, I want to stay at 0 degrees, not. Sorry. Okay, so this is a standoff system in the parlance of programmatic systems. Okay, so here's just, I'm going to show you a bunch of diagrams, so if you're not a dweeb, just go to sleep. Okay. So this is array size. This is the system size from 10 meters up to 1 million meters. This is on the imaginary axis at the moment. This is, I think, where the real axis ends. This is the laser power in watts and the energy delivery per day in megatons. This is the spot diameter in AU spot diameter at 1 AU in meters, so 10 meters, 100 meters. This is the beam divergence in radians. Okay, it's just simple physics. This is why it works. Here's a plot of vapor pressure versus temperature in degrees C, because I had a pretty plot, for basically all reasonable elements. So we've now done the analysis for every element in the periodic table, plus all common compounds that asteroids are thought to be made of. They all evaporate by the time you get to about 4,000 degrees in the most extreme cases. Most of them go at much lower temperatures. We get to much higher temperatures than that, or can. So here's spot temperature versus array size. Here's spot temperature, sorry about that. Here's the temperature, okay. Here's 1,000 degrees, 10,000 degrees, versus various engagement scenarios. The black line in the middle is 1 AU, which is our baseline, so we can engage with temperatures exceeding 5,000 Kelvin. And you don't need that, as I'll show you. Here's the maximum distance to start evaporation. If you want to evaporate, by the way, a comet, you only have to get to about 300 to 500 Kelvin. You can evaporate comets at almost 100 AU, so that would be interesting. I worked out what it would take to put Pluto out of its misery. But I probably shouldn't tell you the answer. Okay, anyway, so this actually, even smaller units are interesting for comets. The larger unit will evaporate any known element and any known compound. Time to evaporate, this is just time to evaporate in seconds. We can evaporate a 500-meter asteroid, which is completely unnecessary, as I'll show you. This is a calculation we ran for silicon dioxide, mass ejection, and lots of other things versus temperature. And there's all kinds of stuff here, so don't worry about too much. This dotted line is the mass ejection in kilograms per square meter per second versus temperature. And you can see it rises roughly exponentially. That's because the vapor pressure is roughly exponential in temperature. Okay. Here's the thrust in newtons per watt. Starts out at photon pressure, which is about 3 nanonewtons per watt, and then rises to about 1 millinewton per watt. And this is simply going from photon drive to ablation drive. This is, by the way, where the common propellants, chemical propellants, live, about 1 millinewton per watt. Same plot in watts per square meter, and we live right around here, around 1 megawatt to 10 megawatts, actually up to 100 megawatts a square meter. Okay, does it work? So here's a little video taken with a thermal infrared camera. I live in Santa Barbara, which is home to the infrared capital of the world. And you'll see some students, which accidentally got in the way here. We have extra students just in case. Here's a picture of visible light. The laser's turned on here. If you watch carefully, you'll see the evaporation starting rather quickly. And then you'll see an incredibly bright spot happening soon. We go completely off scale here. This is not relevant because we're way over scale here. So we're pumping up to about 40 megawatts a square meter in this test. And it works great. I mean, they've blown holes through all kinds of things. The students love coming in the lab with whatever they find, and especially their roommates. Okay, so this is 19 individual lasers phased through a lens back focused onto the system. Okay, so you start vaporizing actually at about 1 to 2 megawatts a square meter. Okay, so we've done all kinds of simulations because we're a university. So this is what we do for a living. Just keeps us off the streets. Okay, so why am I here? I'm here because another use of the system that we immediately proposed was for driving spacecraft. So you can use beam power to drive a spacecraft. And actually, if you look at the plume thrust on an asteroid, just if you want to do that number, it turns out to be about 10 meganewtons for this system, which is about the same as the shuttle SRB, which isn't surprising because the shuttle SRB is about 13 gigawatts of power and comes out with an exhaust speed equivalent to several thousand Kelvin. So it makes sense. This happens for basically any material. Okay, so you only actually have to turn this thing on for a few hours a day to divert large asteroids. You don't have to vaporize them, although for me it's much more fun to vaporize stuff. But okay, so why am I here? Because you can use this thing as a photon railgun, just as John, I think it is, right? John Hunter? Is that right? Yeah. So it's a hydrogen gas gun. This is a photon railgun. Right? So our motto is don't leave home with it. So photon force is twice the power divided by the speed of light if you're 100% reflection. Right? We get about 470 newtons for a class 4 system, which is about 100 pounds of thrust, which doesn't sound like much, but you leave it on for quite a while and you get very high speeds. So if you had a 10 kilogram, 100 kilogram, 1,000 kilogram, or 10,000 kilogram payload you wanted to get to Mars, it would take you 1, 3, 9, or 30 days, which is pretty good. Speed at 1 AU for 100 kilograms is 1,200 kilometers per second, which exceeds the galactic escape velocity. So we deliver a punch, for those of you that are interested in kinetic kill mode, I'll show you in a moment. Speed at the edge of the solar system is about 2% the speed of light. We do have a problem, however. I can accelerate, but this model was built without brakes. But there are solutions. We've designed a thin film reflector in collaboration with one of the companies that we work with to get us 4 nines and greater reflectivity tuned to our laser on a less than 10 micron thick element. So this is real. We don't need nano advances, although that would be fabulous. If I could do this in a 10th micron, you'll see that I can get about 20% the speed of light. Okay, the efficiency is quite interesting. The efficiency per watt is that photon derived from a distance is very efficient in terms of in terms of mass flow, but it's actually incredibly efficient in terms of power. Photons are the least efficient in terms of power, but they're the most efficient in terms of mass flow of anything. Okay, some people use specific impulse in propellants. Typical specific impulse for normal propellants is on the order of a few hundred, up to maybe 3,000 for an ion engine, and photons are about 100,000 times conventional propellant or 10,000 times ion engine. Whatever, so we do calculations just to keep our students busy, keep them out of being committed. So if you like mathematics, this is what this solution looks like. This is time in terms of beta, where beta is V over C. Okay. In the non-relativistic limit, if you take this series out, you get the momentum over force, which is just what you expect. Okay, so what about relativistic effects? Oops, that should have been a beta. Sorry about that. Oh, I know it's because you don't have math type. Okay, so relativistic factors become important when you get to high betas, but at modest betas, doesn't make much difference. But we can get to fairly high betas, but you shouldn't worry too much about relativity at the moment. Okay, so here's an example. I derated slightly down to 50 gigawatts, which is 3 SRB equivalent powers. 100 kilogram payload, these are the various curves, the velocities in green. This is velocity versus time in seconds. Here's 12 days. You get up to several million meters per second, so several percent the speed of light. Okay. So it takes you 15 days to get to 25 AU with the 100 kilogram spacecraft. It takes you 30 days to get to 1 AU with 10,000 kilograms, which is pretty respectable. That's getting close to the shuttle mass. It takes you 1.5 days to get to 25 AU. If I could get a 1 kilogram payload, I'd have to use some sort of nanotechnology for the reflector. And I don't know how to do that, but I would love to have you give me that. That would be fabulous. Okay. Lots of other things here too if you're interested. Okay, so we've actually been looking at various roadmaps. A class 0 system is something that can be built in the laboratory now and actually has interesting tactical uses. Class 1 actually turns out to be extremely useful for space debris mitigation. So we've been talking to aerospace and Lockheed Martin, a variety of people about that. Also has interesting strategic applications, which I won't go into. Both of these can be ground and suborbital tested. We fly suborbital flights at 40 kilometers, so we can actually test up to a 10-meter class system. A Class 2 can be ground tested and would be interesting on the space station. Class 3 is where serious planetary defense begins. Class 2, you get some protection against comets. Class 3, you get quite serious protection. Class 4, you can basically take out anything in the solar system that we know to be a threat. And then I'll talk about 3 other things really quickly. Power projection and high-speed planetary communications. Okay, so if you want to go to true interstellar capability, i.e. highly relativistic, greater than 100-ton class objects, you need to go to Class 5 or Class 6. Okay, but in this case, you go to Class 6, once you leave, there's nothing to come back to. Everybody's gone, right? Because by the time you come back, if you go to the nearest star, well, anyway, there's not much to come back to. Okay, long-range communications. This is really an interesting case. So you can do the quick experiment with an optical link calculation, and what you find is that you get about 10 to the 19 photons per second at each end if you had 2 units 1,000 light years apart. So the typical distance to the Kepler exoplanets is 1,000 light years. So it means we could communicate at ultra-high speed between exoplanets 1,000 light years away. Of course, this is half duplex, because you got to wait a while for the return. But you could stream live from Antares. Okay, here's a link calculation. Basically, the bottom line is we get about 8 megabits per second at 6 light years and 60 kilobits per second at 70 light years. And that's from a spacecraft with a 30-meter reflector, not a 10-kilometer reflector. So you don't need very much, and that's with 10 watts on the spacecraft. So not very large power source on the spacecraft. So we could stream live in a flyby. Long-range power transmission, we get about 50 megawatts a square meter over a 30-meter spot. So for reference, the sun surface is about 60 megawatts. So with 300 AUs, we could get 50 gigawatts spread out over 10 kilometers, which is the same size as the Class 4. So you could actually project 50 gigawatts out to 300 AU, which would be interesting. Okay, so just now I'm going to slightly veer off into the imaginary axis. If you ever heard of Freeman Dyson's attributed, although he regrets the attribution from what I've heard, but the idea is that you build a sphere around the sun, you collect the power, and then some advanced civilization lives on that. But I would claim there's a better way to do it. Why not capture the sunlight and convert it into something truly useful, like a directed energy system? So stars can be converted into directed energy sources like we do on a small scale. And the question is, have any civilizations done this? And if they had, we would surely know about it if they're nearby, because we would have been likely the recipients of the beam. Okay. And classic optics, as I said, doesn't work. You could do an advanced SETI. We know that we can communicate over basically the entire galaxy, not just near stars, with just a Class 4 system, over virtually the entire galaxy. So we could search for narrow line SETI. We could beacon all the Kepler planets quite easily. We could certainly attract their attention. It's as bright as the brightest star in the sky when pointed at a star 1,000 light years away. A planet, say a planet 1,000 light years away, you appear as a star brighter than the brightest star that we have in the sky except for the sun. So ponder what that means. Even in small meter class telescopes at 1,000 light years can detect us. Okay, then there's a whole discussion here which I won't bore you on, which is the technology behind this. But I'll just say the moment the kilowatts per kilogram is approaching unity, it's currently at 0.2. It will soon hit 1, and then it will probably rise to 10 within 10 years. Think about what that means for your future. In your hand, you can currently hold close to a kilowatt. Just think what that means. This laser, 1 kilowatt, you're gone. Okay, just imagine the world in which that's going to come, because it is going to come. Coherence lengths are good. Yeah, not going to get out of here. Okay, here's what they look like. The photon pump efficiency is amazing. It's 85% already. Examples of real systems, simulations we've run of beaming, blah, blah. So there's a bunch of things here we've done on worrying about stability, and I'm not going to bore you with that. Okay, let's just go to the end here. Spacecraft debris we've looked at a lot. We can deorbit things with a class 1 or class 2. If you want to shove things into asteroids, you get about 17 kilotons per shot, independent of the mass, by the way. I know, I'm gone. This thing is completely modular, so the thing that worries me is how to launch the small modules. So if I could use John Hunter's approach and launch them into orbit, I'd finally have a solution of how to get this thing into orbit. We can launch already up to, easily a class 2 can be launched with current propellants. Maybe a class 3, but class 2 for sure. Class 4 don't know how to do yet because it's too heavy. But it's not that heavy, it's inconvenient with the current technology. So we looked at various roadmaps. So new technologies make this possible. There's no technological showstoppers yet that I know of. We've looked at a bunch of issues, including metrology with a group at JPL, among others, and Lockheed Martin. You want to build small systems and let the technology catch up. There's lots of hard technical issues that I won't minimize. I would say it's not feasible to deploy this now, but you could certainly go up to class 2, which is already interesting, and then maybe to a class 3. This is a long-term program with very long-term consequences, and if you're interested, let me know. And here's some of the people that we've been working with closely, and I'd be happy to take any questions.
Thank you so much, Dr. Libin, for a scintillating presentation. Unfortunately, we have run out of time for any questions, but I will just observe that you've made the most effective use of a laser pointer of all the speakers so far. Thank you. So I'd like to introduce our next speaker, who's Andreas Solis, who is also Vice President of Icarus Interstellar, and he will be talking to us about Project Tintin. So I would like you to please welcome Andreas.
Thank you very much. Do I get the... You wanted the PDF, right? Do I get the... Yes, please. Do I get the clicker? Do I get the thing for the slides? Is this it? Hello, everyone. A couple of years ago, we made a mistake in the calculation. And we were playing around when we were working on Project Icarus, and instead of putting 50,000 tons, I put 5. And I thought, well, I'm getting really good performance out of this design here. And of course, a few seconds later, it didn't take too long for me to see that I probably can't get the 65% the speed of light with my little baby Daedalus. We started thinking about what would happen if we put some of the expertise that we've been building over the last couple of years into working with really, really small spacecraft. And I did my master's degree in spacecraft engineering, and then went on to do a PhD in string theory and cosmology. So I always kind of wanted to go back and see what happens, since I left. Is everything okay still back at the homestead? So we started a little project called Project Tintin with a little bit more than just a little bit of tongue in cheek. Which was intended just to be a little toy project to see what we could do with a really tiny, spacecraft, but with a fusion engine and things like that. Really quickly, the fusion engines dropped out, other things dropped out, and we ended up with a design for general principles for a CubeSat mission. Let me see how this thing works. So first we wanted to see what interstellar missions we have going already. So there are some interstellar missions, claim when you Google, what are the interstellar missions that are currently being active. And of course Voyager is one of them. It's got this RTG sticking out off to the side because it's really hot and it doesn't want to touch it. Really needs to stay really far away from the spacecraft. And most of these systems are currently shut off, except I think the ultraviolet spectrometer and the spacecraft is started off with about 420 watts of energy in its RTG, slowly decayed to 260 watts that it has right now. And I used to extract some. I still do this. You know, every couple of weeks I look at the status reports, because every week there's a status report on the spacecraft that's released, and it's currently got about 20 kilograms of fuel left, and it spends about 5 grams of propellant just to stabilize it to be able to transmit back. So, you know, we're just trying to count down to how long the Voyager has, and it's going fast, 3.5 AU per year. But that's not the only one. We've got New Horizons. So there's something that's going to go to Pluto, and afterwards it's going to have an interstellar mission. Probably one of the most interesting things about it, other than that it's also holding its RTG off to the sides because it's also really hot, is that it had probably one of the most spectacular launches, right? So it just direct out of the Earth, it got 16.5 almost kilometers per second. And it won the award for the fastest, for the fastest passenger leaving the Earth. But these are not interstellar missions, though. These aren't interstellar missions. Like when we looked at the spacecrafts and things, these are not interstellar missions, and this is Icarus Interstellar. So we thought, let's make an interstellar mission. Okay, we're not going to go to Mars. We're not going to go to the moon. We're not going to build incrementally. We're going to try and see what can we do right now. Directly interstellar mission. What is the capability? So we went on a search to see what technologies we have that would enable current interstellar exploration. And it happened within seconds, of course. We looked at what can we play with. So we look at CubeSats. They're cute. They're versatile. People do a lot of work on them. They're open source. They have a really nice way of getting around ITAR restrictions because they're used so much in education that you can use the designs. So we started looking at CubeSat technologies and various systems and things. And the two things that we wanted to define is first the hardware of the spacecraft, and second the trajectory. Like how are we going to, in order for it to be an interstellar mission, you have to get it out of the solar system. So we started playing around with some trajectories. And that's kind of how Project Tintin was born. So we formalized the goal of the project is simply being, the objective being to explore the technological trade space for interstellar nanosat missions. As simple as that. We're just exploring and seeing what we can find. So we set some objectives, the science, the propulsion, comms, power, and materials as just a cornerstone, within our team to see. Let's see what we can scratch off, what we need to tackle, what we can just push along a little bit in order to turn this into an interstellar mission, not a planetary exploration mission. So going through them, we start with science. What would you put on a payload on a CubeSat? You'd put some multispectral cameras, definitely some dust and gas collectors. Magnetometers, particle detectors, and something that made me giggle was I think I'm going to scratch this one off because I just found a company in Korea that's selling a multispectral camera, so maybe I don't have to research that all too hard. So let's move on. So let's say science is all done. What about propulsion? Like what kind of propulsive systems can I put on my CubeSat to turn it into an interstellar explorer? I'm going to have to look at interstellar insertion trajectories. There's probably a lot to be said and done there. Am I going to adopt a New Horizons escape trajectory, which is really nice and neat? We go fly off straight into interstellar space, just come and nick Jupiter a little bit, or do I even want to go close to Jupiter? So there was a lot of discussion here because a CubeSat going close to Jupiter is going to have to be shielded, right? So does that mass help me? Plus, am I supposed to go towards Jupiter? Am I going towards Jupiter, or is that a planetary exploration mission? Maybe I don't want to go there at all and save that mass. And of course, we looked at things like the gravity assist and things that maneuvers like the Oberth maneuver that Rob Adams has done a lot of work on, and a really fun and funny maneuver that one of our colleagues, Adam Kroll, calls a flyby. If you try to go really close to the sun. And of course, ion electric plasma thrusters and sails, right? And we've heard so much about sails today that I won't go over sort of our reduction process. Comms is going to be a concern. Comms is going to be a really big problem, because it's nice to have this little small cute package, but all of these planetary interstellar explorers have these really big dishes on them. So I'm going to have to come up with something really clever. So we did quite a bit of work on looking at what kind of things we can get out of low gain antennas, transponders. We started thinking a little bit out of the box. You know, maybe we should have some hybrid designs. You know, band switching for reception and transmission. You know, receiving in K band and transmitting in X bands and things like that. So various things that we could do, and other things like piggybacking comms. Like, is there another mission in the vicinity that we can transmit some of our data to, that maybe they have a bigger antenna and they can send it back, because maybe we're going fast, and maybe even using something like New Horizons, for instance, to relay some of our information. So comms is still an outstanding question, and a really, really quick rundown of defining the project. And then we came to power, and power has always been one of the, when we started Project Icarus, I kind of grabbed the power module because there's so much going on. It's always interesting. There's always tiny innovations that make huge differences, especially when we're talking about extremely long missions. And I'm quite a fan of some of the novel batteries and capacitors and ultracapacitors that have come up, and we've done some studies, especially for Daedalus, that has to charge and recharge fusion initiation power. But we'll hear perhaps a little bit more about that tomorrow. Things like fuel cells, do they really have, maybe there is a place for them on spacecraft. But also power harvesters, solar and solar wind, but my sort of favorite is miniaturized RTGs, and seeing what's going on, like where are these Americium RTGs that people have been talking about for the last 20 years, but you know, no one's built. So these are really the burning issues. And materials. This was around when I was finishing my master's degree. There was a lot of mobility in the European Space Agency with space plastics. They were ready, they were tested, they were going to flight test them, and then they just went away. I think the money just went away, or the principal investigator left, and then everyone said, oh, the guy left the lab with some plastic stuff that he was going to go in space, and someone said that's not going to work, and they put it in a mothball or something. But there was a lot of work apparently done there. Plastics are good things to have in space, especially for radiation shielding, right? A lot of hydrogen and stuff. They could be really useful, especially if we combine them with power that we were talking about earlier. So we had to define a mission. So let's have some fun with this. Let's just try to beat the current interstellar type mission. So the Voyager has been attributed with the first human object to travel close to a star, but it's not actually going there, right? It's not going towards a star. It's flying into the middle of nowhere really fast, and it would have gotten to Alpha Centauri if it was going to Alpha Centauri in 75,000 years. So that's the best we have right now in terms of interstellar exploration. So what if we launched a mission, and this is kind of where the fun, the sort of giggle and the skip in our step kind of went away, and we all felt our mouths a little bit drier, and we started getting really serious about this. Like, let's see if we can actually build an interstellar explorer, and what would it take if we had the money? And our objective would be something simple, like just to beat the Voyager by like a factor of a third. So that's like 25,000 years to Alpha Centauri. It doesn't matter how fast, but it's an interstellar mission. It doesn't matter that we're not going to be around. So where are we going? This is a slide that I always show my astronomy students. Where is Alpha Centauri? It's 60 degrees south if you're close to the equator. It's not up, it's not down. We're in Anchorage, so we're up there in Alaska, and I'm like, you know, it's really, we're even further away from the rest of the people, from Alpha Centauri. What kind of launch would we use? Well, we did some work on essentially playing around with New Horizons' launch with a couple of Falcon Heavies and things like that, the Atlas and the 5 SRBs and things like that the launcher had, and came up with a couple of trajectories and thought those are good, so let's just use those. And then we started thinking of how fast do we need to go to do this. So just some really quick mission analysis. Let's see what we need to frame. How are we going to frame the mission? So Alpha Centauri is 4.24 light years away. We're going to take 25,000 years to go there. It was because that's what our mission was defined to be. So our speed is about 50 kilometers per second. But Alpha Centauri, in those 25,000 years, is coming close to us too. So it's like it wants to be explored, almost, you know. We'll meet you halfway, and it's trying to meet us halfway. So in 25,000 years, it comes halfway there, and my 50 kilometers per, that's per second, right? 25 kilometers per hour. I can do that. Running. The interstellar era starts now. So I just have to do 25.75 kilometers per second, and I got a chance. So, you know, can we do this? Can we do this? Is this possible to do? 3 U CubeSat, because 1 U was probably going to be too small. 3 U CubeSat, let's say 50% of it is fuel. That means that my exhaust velocity, without really showing equations and things, exhaust velocity is, my ISP is 3,700 seconds. And that's when I thought, I thought that this was going to be hard because there's a whole bunch of options at 3,000 seconds ISP. There's a whole lot of options. JPL has made them, Busek has made them, Esta Space, I think it's called, has made one, a whole different ones. These are just some examples. All of these have 3,000 ISP, or 3,000 ISP ion engines, which fit on a CubeSat. Okay, so that's great. I have a propulsion system. And as soon as you say that, you think, still need to calculate some power. Something's gotta. That's the problem here. I still need to give it some power. And if I want to go fast for long enough, so that I can get to Alpha Centauri in those 25,000 years, it's probably going to burn for quite a long time. So what if we burn for about 20 years? It's a bad thing to put equations, but I'm pretending that these aren't equations, they're more conversation points. So you agree, right? So my mass flow is propellant mass divided by burn time, and that's my jet power. So that's how much the propulsive power of the engine is. It's actually pushing. And that's great, because it's still part of the engine. But the energy is the power that the batteries that are attached to the propulsion system for a normal field effect emission propulsion system generally is about 70%. So that means that I need about 7.8 watts, and that's no problem at all, right? Something because that's the propulsion system's power usage. Something has to provide power for the mission's duration. And that's not too much either. But for 20 years, So, can I use solar power? I really wish I could use solar power. But this is relative power from the sun, normalized to solar emission at the Earth. So at Venus we get a bunch, it's really good. At Mercury we don't have any because efficiency of solar panels drops really close to the sun, right? As we go out to Mars, Jupiter, well, we're going to Alpha Centauri, that's not going to do. That's not going to do. So I go back to my favorites. Maybe I kind of wanted to go straight to nuclear power, RTGs. I probably did. So which one was the best? The best RTG that we have is the advanced Stirling radioisotope thermal generator. Okay, that I've been trying to email these people. I don't know, is anyone working on that right now? Because they're not returning my emails. What is the status of this project? Yes. So the power system, mass, if it's got 10 watts per kilogram, from my power system that needs 7.8 watts is 0.78 kilograms. So now I've got about a 10 kilogram 9U, it was 3 before, but now it's 9. 9U CubeSat, and half of it is propellant, 0.7 is the power system. The total engine assembly is about 1 kilogram. These are all kind of normalized to some standards from existing systems because they're approximately the same. And we have some remaining mass here that perhaps the next speaker will elucidate to where this mass has to go, because you have to convert. A DC to DC power converter can weigh probably most of this mass. So you're defining the mission, going back, finding an obstacle, go back, refine it, go back, define an obstacle, go back and forth until you've got a mission. So the trade space really for CubeSats, interstellar CubeSats, is defined by what I'm plotting here is there's 2 axes, specific impulse versus travel time to Alpha Centauri, because that's interesting, and power source, the specific figure for the power source. So really, we're somewhere down here, right, at 10 for the ASRG on a CubeSat. And if you want to make good time, as in 10,000 years, you need space nuclear power on a nanosat. Difficult. But there are propulsion candidates still. So I'm just going to go over this really, really slowly. This propulsion system, an indium ultra FEEP, has been my favorite for the last while. We've been discussing. We've become good friends with the team that's developed it. It's a gridless design. It uses indium, so the propellant can be stored unpressurized, and it's in solid form. It's not toxic, so you can play around with it in the lab. And as the same potential that emits the indium ions also melts the indium. And it uses something called the Taylor cone. So you know when you turn on the tap, the water, and you just turn a little bit and it makes this nice stream? That's called the Taylor cone. So they do this with this indium, and a nice stream of indium comes out. And it's a really remarkable design. So we're sort of out of options for the advanced, the ASRD, the Americium RTG, an Americium RTG was developed after I left, of course, from Leicester University, which is where I did my master's, and they've got about a watt per kilogram out of them. But that would be really cool for like, dare I say, planetary missions, or like really long interstellar missions. And I just have 2 minutes, so I'm going to skip over the comms and just show some renderings of what we came up with for the mission. This is an array of 16 ultra FEEP engines, and and one of the CubeSats with radiators in the middle, and the other one holds the brains and things. And I will leave you with this slide. Do you want to play it? If we have time? Yeah. What, you can play them, yeah. So this is a beautiful rendering that Adrian Mann made for us. He's the person that made most of those amazing renderings that we see in the corridors. And there's one more that's a neat flyby. So here it's deployed, and there's these tiny little booms here, and we were thinking of using the sides of the solar. They're not quite solar panels, but they're for communications, so we would reflect some of the signal on there. So some people have started doing some work on that, using the solar panels as collectors for telecommunications. But it seems incomplete, so we're working on that right now. This is, and I'm finished now. Okay, I'll just stop instead of trying to tie it up. Thank you.
Thank you so much, Andreas. We've actually got 2 minutes for questions, so if there's a couple of questions that can be phrased and delivered very quickly. There's a question right at the back, towards the back there. It's a guy in the blue shirt.
Why don't you guys just use a multi-stage rocket? If you just need 25 clicks per second, just go eight 3-click per second stages, and you're done. That's only a metric ton or so.
You know, I didn't hear the question
No,
very well.
yeah, I'm not an electrical guy.
I think it was more a statement of how we can solve this problem.
Yeah, no, I mean, if you want to deliver 1 kilo to 25 kilometers per second, just go 8 stages at 3 clicks per second with ordinary RP1 and locks, and this is solved. You don't need to, in other words, you don't need to go electric propulsion. Just go 8 stage.
I think there's one more there. Thank you for that question.
Have you considered flying these things in a configuration with several of them going out at one time? And I assume you're going to use laser communication.
Yes. So the Project Tintin and this whole CubeSat effort has always meant to be something that we would progress. So we'd try some low Earth orbit tests. We'd try to build Icarus's space hardware capabilities and experience and things like that. We've been thinking of doing tests of some of the problems that we would have with Icarus at the target star and things like distributed networking, and try to test them on satellites, especially things like how the mothership on arrival would communicate with the probes and things like that. A really cool idea was to send some CubeSats out, and they're not on solar system escape, but we would switch them off, and then they would come back in towards the Earth, and they would start exploring the Earth and the Earth-Moon system without knowing that this is the Earth-Moon system. We would test the computer systems basically to see how they react. Does that answer your question?
Okay. Thank you so much, Dr. Sellers. No more time for questions, and I'd like to introduce the next speaker. Next speaker is Bernhard Seifert, who's received his Master's in Physics from the University of Vienna. He's involved in the field of electric propulsion research for 10 years and is now working with, is a subcontractor for a couple of space agencies, and he's been doing that for the last 3 years. Bernhard Seifert is going to come and talk to us about innovative ultra FEEP, is it that or is it FEEP, thrusters for interstellar precursor missions. So thank you very much.
Yes, thanks a lot for the introduction. Andreas already took some of my topics for my presentation, but either way I give you a short overview. At first start with a quite complicated title. So we are focusing on ultra-FEEP development at FOTEC, and in special normal FEEP technology, and ongoing to very high voltages, as you see later on. We are going forward to ultra FEEPs as well. So just to give you a brief historic overview of the Voyager missions. So these were the first missions which exceeded our solar system. So the Voyager 1 is just doing this at the moment. And these are just the past missions, but I will give you also the demand for future interstellar missions. So for example, what will be important in the future will be the investigation of the interstellar medium, or the analysis of the cosmic radiation and the risk for human spaceflight. And for example, also the investigation on dwarf planets or the Oort cloud. So this table here gives you a short overview of the propulsion systems which are available today. So on the left column here, I'm not sure if you see the laser pointer quite well, but yeah. We have here the, for example, chemical, nuclear, electrical, and also propellantless, which might be a photon rocket or solar cells, as we have already here today. And this just gives you the certain ISP values. Just for the definition of the ISP values, we have it here. So the thrust is mainly the mass flow multiplied with the exhaust velocity. And if we replace the exhaust velocity with G0 times the specific impulse, we get a definition for the specific impulse here. And we see that electrical propulsion systems and of course propellantless propulsion systems has the highest ISP here. So we are reaching up to 10,000 seconds for electrical propulsion systems. And as you see here, the thrust levels, which are comparatively low for electrical propulsion systems, and the highest values here we get of course for nuclear and chemical propulsion systems. So now how does this apply to our mission demands? So depending on the mission, for example, nearby planets, outer planets, and so on, we have certain delta V requirements. So, and also certain ISP requirements here. So let us just take a look to the nearby planets. Here we need ISPs of 10,000 and more. And if you're going on to outer planets, we have, sorry, there's a typo here. For outer planets and going on to the Oort cloud and interstellar, the required ISP, of course, is increasing more and more. Also the delta V, of course. So what we are seeing here, we need for an interstellar mission at least ISP of 100,000 seconds. And this is quite a lot. So as you've seen here before, the best propulsion systems so far, the electrical ones, are only reaching 10,000. So there is far a lot to investigate and further on. So we have ion thrusters used for some of the past missions. So for example, Deep Space One Dawn, Baby Colombo, and so on. So they all used ISP values of some thousands at least, with the thrust levels reaching between 90 millinewtons and going up to 670 millinewtons so far. So now we will focus on the electrical propulsion system we are currently developing. This is the field emission electric propulsion system. So Andreas already explained the basic principles. So we have a solid propellant. In our case, this is indium. Why is it indium? Indium has a quite low melting point at around 156 degrees Celsius. And it's done like this. So we have here a propellant reservoir we are melting it to this temperature, so around 170 degrees, just to be on the safe side. Then we apply here a high voltage, and we are extracting the ions directly from the liquid phase. So the Taylor cone here is building up due to the high electrical field strength. And due to the Taylor cone, the field strength is almost increasing anyway at the tip here exactly. And that's exactly where the ions are extracted. And later on they are accelerated due to the applied high voltage. So it's just a one-stop technology. We don't need at the first step to generate the ions, and later on we accelerate them, but we're just doing this in a one step. Yeah, and in our case we have demonstrated ISP's values of up to 12,000 seconds. This is quite remarkable. And due to the use of the low temperatures, only 170 degrees, also the heating power is very, very low, and we have only low thermal losses due to isolation and radiation. And of course, indium is a non-toxic material, and the advantage of the solid propellant is, of course, that you don't need heavy propellant tanks, valve, pipe systems, pump systems, or whatever. So it's quite convenient. And we have moved on our technology. So in principle you have a normal needle which consists of tungsten mostly. And the problem with this, you have a very thin layer on indium on this needle. And when you switch off the heating power, of course the indium gets solid again. And it might happen that the indium film on this very thin indium film is broken, and then the FEEP emitter might stop working. So that's why we changed our design a little. We are now using porous needles, which means we have sintered tungsten, and this is a porous structure here. And the advantage of this design is that we don't have indium just on the outside of the needle, but also within the needle itself. So this strongly reduces the risk of dewetting and keeps the emitter in proper operation, even due to thermal cycling. So in this case here, we have used 28 independent needles. You see the size here, so it's very small. That's less than 1 centimeter in diameter. And our nominal thrust will be around 300 micronewtons. If we go up to higher voltages and higher currents, we can also achieve 1 millinewton. But of course, then the efficiency degrades, and also the lifetime of the needle. I will show you a short video how this firing process of the FEEP emitter is going on. So you have seen on the left the picture with the 28 blue dots, and we are now seeing here this ground emitter in a vacuum chamber, and we are increasing the voltage more and more, and you see one needle after the other starts firing. So it only depends on the applied voltage and on the generated electric field. And you see here it goes in a row, and at very high acceleration voltages up to 20 kilovolts, we can achieve that every needle is firing here. And you see the blue plume here. So we have a very high current of more than, let me think, I think 20 milliamps. So we have an electrical power of up to 400 watts. And at this small size, this is quite remarkable. And just to go back to the Tintin mission, we are also able to fit our FEEP module in a CubeSat here. So what you're seeing here is a 1 unit CubeSat, and this is filling up to only the half of the 1 unit CubeSat. And of course we had to reduce our design a little. We're only using 40 needles for this due to the limited power budget, of course. And the nominal thrust is reduced from 300 to only 100 micronewtons. And the mass efficiency for the system is around 30% with an ISP of around 3000 seconds or more. And of course you won't be able to operate it in a one-unit CubeSat because of the remaining subsystems, DC-DC converters, communications on board, power systems and so on. But just to give you an overview, it is possible to reduce it to this size. Okay, Andreas already told you about Project Tintin, so I'll skip this. And now the main considerations, how can we increase the ISP? So we've seen for the most interstellar missions a very high ISP of 100,000 seconds or more is desirable. And here we get around the propellant velocity, again the relation to the specific impulse you see here. And we have here mainly the charge of the electron, the acceleration voltage, the mass of the ions, and here we have the efficiency factor. So for the efficiency factor we are considering droplets, the beam divergence and other factors as well. But what you can see here is that the acceleration voltage is, the square root of the acceleration voltage is directly proportional to the ISP value. So that means we have to use this very high, for 100,000 seconds we need several hundred kilovolts of acceleration voltage. And this is very, very hard to achieve on a CubeSat or even at a normal satellite, a large scale satellite. Of course, when you say you need several hundred kilovolts, they ask you if you're crazy. And of course the reason is this: for the electrical insulation is causing lots of problems. So we have, for example, outgassing of various components which could lead to spark throughs. We have also the thermal losses in such a satellite. Or for example we have the X-ray radiation. When you can imagine we have 100 kilovolts or more, we have a lot of electrons which are attracted to our crown, which are emitting X-ray radiation, of course, which could harm the materials around. So it will be necessary for future research to find out how to reduce the material stress. And what we also have is grid erosion, of course, which means that, as I told you before, we have a certain beam divergence, which means that not all ions are expelled out of our thruster, but some will directly go to our extraction grid, which means this grid will be eroded. And this, of course, we need to avoid somehow. This just gives you a short overview. For example, when we want to have here 100,000 seconds, and we assume, for example, an efficiency of, let's say, 80% of our thruster, we need around 900 kilovolts of acceleration voltage, which is quite a lot, of course. So what are our next steps? Our next steps are we make not just one needle, as we have shown you before. We can use a 1D array, for example, a ground structure, or a 2D array, which looks like this. But of course, if we make an array, it's hardly feasible to use an extractor for every single needle. So that's why we moved on to just to be sure, we need an extractor of 4 to 8 millimeters. So if we use this for every single needle, so the size will be very, very large, and we won't be able to fit a lot of single needles on a certain area. That's why we use an high electric field forming electrode system. So we're introducing here special electrodes which are forming our potential of the electrical field like this. So every needle is experiencing the same electrical field as if we applied a single grid to it. And this avoids the use of a grid and of course the erosion problems we've seen so far. This is just a concept study of such a module here. Here on the right we have already built such a system, just with the difference we have here the 2D grid and here we have the 1D crown FEEP. Yeah, this area here is a surface area of around 150 square millimeters, and we are fitting it with 122 needles. And if we apply acceleration voltage of 120 kilovolts at 50 microamps per needle, we can get around up to 3 millinewtons at 30,000 seconds specific impulse, which is quite a lot. So the issues I've already mentioned. Okay, the issues I've mentioned before are the X-ray radiation, of course. So when we have 100 kilovolts or even up to 700 kilovolts or whatever, the X-ray radiation is very high, and we have to get rid of them at least, or we have to strengthen our materials there. So what we could do is we use magnets to trip the electrons and to deflect them. With ions, of course, it's not possible, but with electrons it should be okay. And our conclusions for this is, so we've developed so far the indium FEEP technology, which is giving up to 100 kiloseconds of specific impulse using a 2D array. And technology has already been demonstrated in our labs. And in our next step, we will move on to the ultra FEEP technology, where we can further increase the acceleration voltages and then reach the demands of our 100-year Starship mission requirements. Okay, I will skip this now. Okay, that's for the intention.
Thank you so much for your talk. Unfortunately, we've got no time for questions. And now we're going to have a 15-minute break. Heath, you're going to be announcing something about the evening event. But essentially, we would also like the participants for the General Assembly to come down to the front of the podium after we're done.
Thank you. Excellent. Oh, this is a sharp mic, isn't it? I do hope you'll join us later on at 8 p.m. for Stakeholder Stage. It'll be a celebration of the impact of DARPA 2011, a conference that's had a great impact on all of our trajectories, whether we know it or not, I think. We'll be joined by Mark Millis of the Tau Zero Foundation, Daniel Sheehan of USD, Joe Ritter of the Maui Institute for Astronomy, David Weiss at Eck Industries, and Paul Gilster of Centauri Dreams. Actually, Paul, are you here right now? I haven't found Paul. Hello, can you check in with us just before dinner? We're going to touch base on it as well as the speakers go. So I really hope you'll join us, and I look forward to the evening, and the General Assembly is next. Thank you.
Thank you. Yes. Yes, so 4:30 we'll start with the General Assembly. So could all the participants come down to the front, please?
All right, everybody, let's get seated, please, for the General Assembly. I would like to introduce everybody to Dr. Anu Bowman. She was formerly with the Foundation for Enterprise Development, but I think she's an independent consultant now. Is that correct? She is the Secretary General of the General Assembly of the Starship Congress Near-Term Questions, and she will be chairing for the next 90 minutes. So I would like to welcome Dr. Anu Bowman.
Thank you, thank you. First thing, we've had some really nice technical conversations, technical discussions today, technical presentations. This is something a little different. This is a conversation. And we can't really have a conversation with everybody in the room with everybody so spread out. So let me encourage those folks in the back to move up, because this is participatory. So please, let's get a little intimate, let's squish in, not as much as we did for the picture though. And while you're doing that, I'm going to go ahead and explain to you what we're doing. So this is a panel discussion addressing specific questions that were posed in advance to the leadership of the interstellar organizations. There'll be 3 questions discussed today, 3-minute responses by each of the participants, and then discussion that's open to everybody of each question. We're going to try and keep very tightly to the time so that we actually have time for discussion. Today we're covering the interstellar now, next 20 years. Tomorrow we'll cover interstellar current generation, the 20 to 50 year time period. And then on Saturday we'll cover the future, 50 years and out. Please note, it's not a debate, but discussion is heartily encouraged. So our participants are Jim Benford, representing Starship Century, Les Johnson, the Tennessee Valley Interstellar Workshop, Kelvin Long, Institute for Interstellar Studies, Mark Millis, Tau Zero Foundation, Rich Abusi, Icarus Interstellar, and Joe Ritter. Joe? We're looking for Joe as we speak. And Armen Papazian from Star Voyager. So, well, okay, maybe he'll come before I'm done talking. So I'm not going to read each of these questions now. I'm going to encourage you to look at your program. The questions are listed on the opposite page of the actual schedule for each day. But today, I already told you what they're about. So, at the end of the activity, the compiled responses from each group will be published in a special edition of JBIZ. And the next session of the General Assembly, Starship Congress, will reconvene at the 2015 meeting. So, with that, this is today's question, or the question right now, and the topic is the economy. Space exploration is a costly endeavor. Missions to stars will likely cost significantly more than any other space project or mission that humans have ever engaged in. Given the likely costs involved, how do we get the funding to pursue interstellar research and development to the point where interstellar travel becomes credible? Jim.
Let me say that Starship Century is a very small organization. My brother and myself, and the intention of Starship Century is to address the fundamental problem in interstellar research, the lack of funds. And so the Starship Century will produce profits which will be given to fund interstellar research. The book that's on sale out there, profits for that book go to interstellar research. The book is the first product of the Starship Century. So to address this question, interstellar exploration will follow from the development of an interplanetary economy. Funding for interstellar research will be scarce unless we work backward from interstellar applications to near-term space applications that can be funded. They'll be funded because they make economic sense to the investors. Therefore, interstellar community should be looking for those applications and soliciting funding, hopefully from private investors, to pursue those. That is in contrast to going to the government, which is very susceptible to arguments at this point that interstellar is too far off to think about now. They've got lots of other problems and commitments of funds. Consider, for example, the development of Antarctica, which started over a century ago. Although the pole was reached early in the 20th century, it was a half a century later before serious exploration was possible. because the technologies didn't exist to operate in the environmental extremes of the cold, the wind, and simply the remoteness of the continent. They didn't happen till then. They weren't available, but they were later. Robust air travel, radio communication, transportable energy sources, and things we don't think about like the existence of large, reliable parachutes. But for this century, 3 technologies stand out as apparent in the development of space. First is space robotics with advanced AI. We saw a lot about that today. Another thing we're going to need is nuclear thermal rockets, which we've already developed, and really they provide the thrust to get serious payloads out into the solar system. They're the inevitable solution we have to go back to. And finally, 3D printing. We heard a lot about that today as well. These are the physical inventions, but there will be many more that are not physical, and much else will be necessary in biological sciences if we're going to have humans getting off of this ecosystem and into the solar system.
Thank you, Jim. Les?
Yeah, to begin with, unfortunately, barring miracles or major surprises, there really is no way that interstellar travel will become credible in our lifetime. Don't shoot me, I said travel, I didn't say research. Research on the topic can and must be credible, but that's about as far as we're going to be able to go in the near term. Fortunately, research and development is not necessarily expensive, especially the research part of it. If Robert Goddard were alive today, he'd almost be a maker in the sense that hackers talk about makers. The difference between interplanetary and interstellar travel at this stage of our development is really negligible. We believe that organic, self-sustaining space development, a space economy, will ultimately bootstrap humanity to the stars. That said, I have a personal bone to pick with this assertion that space travel is inherently that expensive compared to other things that we do. Yes, from the perspective of you and me, a space travel, a space journey, a space project is expensive. But from a societal point of view, not so much. For example, the Brooklyn Bridge cost $15 million to build in 1883. This would be about $350 million today. That's about the cost of a small satellite in Earth orbit. More importantly, 27 people died building the Brooklyn Bridge, and that was just the price of progress. I'm not saying we ought to be killing people in space exploration, but what I'm saying is that we've become a risk-averse culture, and that's something we have to be mindful of. We don't decry the cost of building a bridge across a river, but we do when we talk about bridges in space. If we contend that becoming a spacefaring civilization, which will be required to mount an interstellar voyage, is simply a matter of priority and politics, external and internal. That said, we should pursue funding from all possible sources, public and private, and leverage related research as much as possible. To give just one add-on to this, pay attention to a news broadcast every time they talk about something that happens to do with space exploration. They always give you the cost. And they don't do that with everything else they talk about, but they always do, and we walk right into that trap because we always say what we do is expensive. The U.S. federal budget this year is over $3 trillion. That's 3,000 billion dollars, okay? A Mars mission would cost a fraction of that. Bootstrapping us to becoming an interplanetary civilization is a small fraction of one annual budget from the United States. So I think we should not allow that our area of development be painted as, quote, expensive, and we shouldn't refer to it that way. It's not that expensive, it's a matter of priority.
Kelvin?
Thank you, Madam Secretary. Fellow Congress members, so I'm just going to go ahead and read the statement from our team. The pursuit of the interstellar goal requires a strong foundation, and this includes financial sustainability and growth. In order to generate financial resources, which will pay for the development of Starship technologies, any organizations need to also look at spin-off activities, which lead to the emergence of new technologies and associated activities, patents, inventions, processes, or tools. This requires the cooperation of for-profit entities, and so for the future, we clearly need to bring corporations under the umbrella of interstellar studies, rather than the current situation of only non-profits dominating this subject. There are things that non-profits can do, such as running crowdsourcing programs, creating strong advocacy for space among donor bodies and governments, publishing research achievements which illustrate the progress. They can also engage the entertainment and gaming industry, and particularly the movie industry, to gain appeal to the masses. They can engage multilateral bodies like the United Nations to raise the profile of the subject. But ultimately, the shift should be to move the discipline of interstellar studies to a commercially driven industry rather than a purely voluntary vocation, with strong global networks and cross-cutting appeal. In order to facilitate that, the existing organizations should focus on the development of sound business plans and strategies, which clearly shows the return on investments both over the short and long term. The road to the stars cannot be achieved through charitable activities alone. The most important long-term goal is to see the industrial civilization itself continue to grow, thus providing both the technological capabilities and the economic surplus for interstellar ventures. The unique selling point of interstellar research is that we demonstrate where industrial civilization is headed as it continues to grow. That research should continue to attract funding on that basis. In summary, our answer to the question is that through the continued growth of industrial civilization out into the solar system, creating new wealth into space itself. Thank you.
We were taking the tactic of, rather than advocating for big bucks, figure out what we could do with the resources we already had. And that meant finding the pioneers who were actually working on the edgy stuff anyway, in addition to their day jobs, and then also trying to package things down small, like, for example, trying to find what were those next step research things that could be done at the level of a graduate dissertation, and then try and get scholarships or some other educational funding to have graduate students do that, and also then disperse the work, because as yet there is no centroid of expertise in this topic, and it also covers a lot of different disciplines, including the sociological elements that aren't all in one place. So the kind of strategy that we had in mind is, just get things rolling with small amounts, and then build a foundation of credible progress to demonstrate to any potential future philanthropists that we could indeed deliver meaningful progress in a economically wise fashion. And then once that foundation was impressive enough, to seek larger donations where then we would have enough to actually solicit research. You do have to echo what Les said about the actual research, especially compared to other stuff, is not expensive at this point. And then when you try and estimate how long we'll be ready before we can actually launch an interstellar mission, at our current rate of procrastination, it looks like 2 centuries. So the idea of ramping up right now, I don't know if we can do that. So our tactic is to build from what we can until it looks like we've got enough to work with to up the ante. Thank you.
Let me begin by thanking our fellow delegates for participating in the first General Assembly, and by paying thanks to the Secretary General for hosting this event. So the question asks, how do we get funding? And I think if anyone at this table knew the answer to that, then we'd be building the Icarus today. So I think the crux of the question is, how do we incentivize funding? So I want to address this question from the context of how do we incentivize funding for an interstellar mission? And I think that this can be framed in a conventional sense first, and then a disruptive sense second. So first of all, from the conventional sense, what's going to incentivize broad swaths of the population and governments to fund interstellar mission? And I have 4 points. The first, I think that certainly investment and study of astronomy, specifically the future discovery of an exoplanet, an Earth 2.0, if you like, something that is an indisputable second home, I think that's going to really incentivize a large fraction of the population as we see a tangible goal, something that we can, ultimately shoot for. Again, a little out there, but I think indisputable evidence of some kind of signal from an intelligence not from this Earth would be something that would incentivize funding into interstellar flight. Again, proof of some kind of an irreversible catastrophe that would render the Earth uninhabitable is something that would incentivize large-scale funding into interstellar research and missions. And second, some unknown profit motive, some kind of unobtainium, if you've seen the film, I think it's Pandora, that would offer significant return on investment for investors. So that's the question framed in the conventional sense. On the unconventional or semi-disruptive sense, I think that we may be on the cusp of a new era of space funding. Starship Congress is an example of that. We raised close to $16,000, which helped us host this event. Planetary Resources, with its Arcid space telescope, raised $1.5 million via crowdsourcing. When are we going to see the first billion-dollar crowdsourced project? I think it's going to happen in the next 10 or 20 years. Could the first manned Mars mission be a crowd-funded mission? So I think, in summary, I think the crucial theme for us to examine is how do we determine the value proposition of interstellar flight, and something that's going to inspire large swaths of the population to support our vision. Thank you.
Thank you. I'll be presenting Star Voyager, but the ideas I'm going to be sharing with you have been published in a Star Voyager roadmap, but also are my personal publications and authorships, which I actually will be presenting tomorrow. So they're linked to the Star Voyager position on the economy and how we're going to finance interstellar travel. My perspective is a bit different. I believe the real issue and the real challenge we face is not to convince or governments that they need to give us money, or convince billionaires that this is a good deal and this is good for our own evolution. I think we need to be a lot more aggressive than that. I think we can't just, this is about human evolution at the end of the day, and to subcontract that to a non-structured solution is not the right way. And the proposition is that we need to change the way we create money on Earth in space if we want to get out of the solar system, period. Why? Because our monetary and financial imagination is just as important as your technological genius. And all of you here, I've heard a lot of beautiful things today. And by the way, you can add economists to that gas gun alongside the attorneys that you were going to put in, because we've got a lot of trouble there too, and central bankers as well. To sum up, we need to change money mechanics. We need to change the logic of money creation from debt to investment. We need to reinvent the way we actually see money and how we allocate money. And it's, yes, it's good to have a crowdfunding effort that raises $1 billion. That's a potential lesson. But there are, right now, this month, $85 billion of pure invented money was given to the banks in Wall Street, while at the same time, the banks were sued for not being able to upkeep standards when they come to the sale of mortgage-backed securities. They've been sued because they are messing up with the energy market, and they have been given the like Enron title. It's all on Bloomberg, you can check. Houston has recently filed a lawsuit against the banks who actually made them lose money because of the manipulation of the London interbank offer rate. And yet the Federal Reserve gives them 85 billion of invented digit every month, but NASA's budget has to be cut. This absolutely absurd, and excuse my French, it's quite retarded way of doing things. In 2013, and I'm not talking about the science of it, I'm talking about the mechanics of being able to fund interstellar space with free money.
Thank you, Armand. Go ahead.
Sorry.
Hi, I'm going to give 3 different answers to this. So, first of all, is it credible now? I don't think there are many of you in the audience that will say that it's not. It's just very long term. I'm of the opinion we'll be sending DNA first, and in fact, there was an interesting study that came out a few months ago where they essentially applied Moore's law and plotted genetic complexity of life forms on Earth versus time, and that seemed to indicate that DNA was much older than Earth, possibly, and so I'm just going to throw something out there. I think that we already know it's possible because we are the space probes. And that may sound a little bit out there, but the DNA evidence suggests that's one possibility. And small payloads are on the horizon now, even with things that we saw today, like solar sails. So credible now, Already, yeah, I think so. Just difficult in the long term. Now, as far as funding, long-term development depends traditionally on government things. And unfortunately, we see a lack of vision in many areas in our life. There are a lot of companies that want to return in 3 years, and governments are supposed to propel this long-term vision stuff. However, I don't always see it happening. I won't be negative on any particular programs. So I don't think that will work. Clearly, private development of things like initially a cislunar economy now is essential. And the real answer to the question, I think, is to look at dual-use technology. Things that are needed on a Starship are needed on Earth. Life support, medicine, recycling, information handling, robotics, all of these kinds of things, there's a lot of money to be made on Earth. And so I think ultimately, and what was part of our 2011 proposal, was to have an ecosystem of businesses that are working on dual-use technology. And if people think they will make money on things, then money goes in and money goes out. So I think ultimately, it's got to be motivated by, I hate to say it, profit. And I think that's possible with private sector.
So let me thank you for the answers to that first question. And I'm just going to make an observation, and that's that this was all very polite, and that's good. But there was actually a fair amount of disagreement in terms of just approach. I heard, okay, let's focus on what we can do with what we have now, and try and educate and motivate students, and that's good. I heard we need to be much more aggressive with just changing the way the world views the economy of space, if you will. Surely there's some other comments or questions from the audience to poke at this or contribute to the conversation. Let me throw it out before I ask a question. So you have to speak up because we don't have a mic in the audience right now.
budget that they themselves as a group would put together and use their own lab space and production time to do, rather than, say, having them donate and then wait for something to come around. As I know, there is a lot of drive towards wanting to run experiments themselves and possibly seeing the own implementation themselves and then turning it over to a general population.
So do you want to direct that at anyone in particular, or do you want me to pick?
Whoever would wish to tackle it first.
So Rich, you go ahead. And then,
I think that hacker and makerspaces are a vast untapped potential. I'm proud to announce that Icarus Interstellar recently, through the activities of our Vice President, incorporated an Alaska, an Anchorage-based makerspace to help us make progress on interstellar-related engineering projects.
So I'm just...
Kelvin, just a second. Go ahead, Joe.
Okay, I'm an academician, and by definition, a lot of what I do is open source. I'm going to take off my academic hat and put on my Space Gambit hat for a moment. So I'm on their board. And I will give 5 of my 10 minutes in presentation tonight on Space Gambit activities. But there's clear recognition that this takes global teamwork. And so Space Gambit, very quickly, the history is that they applied for the 100-year Starship money from DARPA and were unsuccessful in that, and DARPA came back and said, well, put in a proposal. So this is also centered on Maui, although it's a global effort. And they got about $500K. So far, we have funded, well, let's see, we had approximately 50 projects submitted, including Andreas's project. And we selected 9 of these projects to the tune of initially about $130,000 for supporting this. There will be a second round later, and we can talk about this later. There's wide recognition that open source has to be done for this, and in fact, our Global Starship Alliance and Open Source Starship Alliance held an open source space technology TED last year in conjunction with some other organizations. So yeah, hackerspaces, great, absolutely, yes, we're trying, we've actually done this some, we want to expand, let's talk more about it. I'm all about open source, I think it's great.
Thank you, Joe. Calvin, go ahead.
So I think that these ventures such as Hackerspace, Makerspace are wonderful initiatives which are providing a fantastic opportunity for public participation, in particular in the journey of space, which arguably in the past hasn't always been there because it's been so expensive. But we must keep an eye on the ultimate goal here, which is to create a civilization which is interstellar capable, which means we can send humans to other star systems. That clearly requires an industrial complex, a solar system-wide economy. I personally don't believe that you can get to that position based on those sorts of ventures alone. I think they're wonderful for education, for seeding new ventures, and for creating participation. But ultimately, in order to create that self-sustaining economy in space, to grow the infrastructure in space so that we can move on to the stars, I think that this does require for-profit ventures. The activities happening at the moment in the commercial world, such as SpaceX, I think really illustrate that point. The problem is these things are very expensive. And so hopefully these other opportunities will allow a bridge for the rest of us to get involved in those activities. And ultimately, I think we shouldn't be afraid of the opportunity for people to make money if it's going to further the mission and provided it's done on a moral and ethical basis.
Mark?
Okay. About the hackerspace, I mean, that goes right along the theme of using resources that we already have, which, hey, I think is cool. And also, I was a hacker before it had a cool name. Back when it was talked, you were a tinkerer in a garage kind of thing. The other part is I'm not sure how much of the true interstellar challenges hacker groups can handle. And after thinking about that, the one that I realized that is actually well within their type of resource level and really needs a lot of playful work is closed loop life support on every facet of that, from food to waste to air, and even, you know, talking about closed loops of people and how well they behave. And that's something that can be done in small groups. But can you build your own fusion engine? I don't think so.
So I think we have another question in the audience.
Actually, simply a point of information on Kelvin's note. There's nothing in the open definition that's put forth by different open source advocates that precludes making profit from those from open source software. It simply precludes keeping others from repeating the work, so it removes artificial scarcity, and that's actually all.
Thank you. Back there, yeah.
I don't know if this is necessarily a question or a comment, but when we talk about the global space in the sense that, you know, every country across the earth is supposedly in cahoots to get us to a space-faring civilization. The reality is a handful of individuals that are really, you know, for instance, this room, we have people from France, Argentina, Japan, U.S., Mexico, across most of this planet. But what would it take, for instance, to unify the true world, the tier 1 group, the tier 2 group, the tier 3 group, unify those civilizations to really make use of all? For instance, South Africa, for instance, you do forgings and castings there all the time. What's it going to take to necessarily bring those groups into a sense of understanding that this is a project, this is an undertaking that will really make a difference for humanity as a whole, and not just a collective group of individuals who see it as a dream and a vision? Does that necessarily make sense?
Yeah, thank you. Thank you. And Armin, go ahead and take that one, please.
Well, first of all, I happen to be the chief executive of a joint venture called the International Space Development Hub. Basically, our aim is to create a synergy center on a global scale to create a physical as well as a virtual platform where we can channel innovations and investments into space. And we intend to locate this in Moffett Field, Silicon Valley, in Hangar 1, where there is currently an open RFP. And the reason I'm saying this is because to unite the world, which is, you obviously need platforms of connectivity on a virtual level, but also you can have a physical location where you can bring all the different agencies of the world in one location, allowing the creation of a real hub so to speak, to stimulate and create that buffer, the commercial buffer that needs to develop to take this industry forward. So that's one attempt in which we could really make this not just a group of individuals across the planet, but actually create an integrated platform where these people and a lot more can plug into, because individuals cannot plug into NASA as such, but or small ventures cannot necessarily entertain big, large players. But once you create a hub, when everyone can come in from across the planet, then you've facilitated that. That's just a step towards that integration.
Right, so I mean, it's along the lines of essentially the Kennedy administration back in the 60s that actually unified and said, hey, we're going to do this and make it very coupled. So the question then becomes, do we need something more pronounced, you know, like that hub, or a catastrophe, or a
Enlightenment.
just an overall realization across every country, every nation, peoples, to really get us to actually move on this.
So on that point, Les, why don't you take that, but make it short, and we're going to move to the next question.
I attended last year a gathering of well over 100 of the next generation of international space leaders. And I won't mention the gathering, but I was asked to give a talk there. And while I was there was a discussion of these for-profit companies, which everyone here has talked about as an essential part of opening up the space frontier. The consensus among that group, which terrified me, was that that should be banned, prohibited. Don't make money off space. It belongs to the entire planet. It's the province of humanity. How dare anyone make a profit there? So I urge everyone here to be aware, wherever you stand on the spectrum of space development, and I've heard here a pretty broad consensus that it needs to be basically open to all these different approaches. There will be active opposition to that. And I've heard it, and I've seen it, and it scares me.
So let me ask everyone else to hold your questions. We're going to move on to the next question, and I'm sure there'll be other ways to weave your thoughts into some of these. So question 2, investing in the future. The majority of past space exploration achievements have been enabled by the pioneering attempts from world governments, particularly the USA and the former USSR. We are now witnessing the emergence of a commercial space industry and space tourism. Would the establishing of deep space mission capabilities, including human, be better facilitated by government, commercial, or hybrid leadership towards interstellar space exploration? Jim.
Well, actually, I think that the events of the 20th century, in particular the World Wars and the Cold War, changed, perhaps temporarily, the way in which development occurs. Remember, the space race was a political competition, political, economic, ideological competition. I don't think that's not the future. That's the past. But to answer the question directly, and I will elaborate on what I just said, clearly development is going to be private or public, that is government or the enterprise system. It's clearly going to be a hybrid involving both the commercial sectors and government sectors, but we should also include adventure activities that have nothing to do with making a product, but rather with having an experience. And I think that's going to be very big in low Earth orbit in the very near future, and suborbital even future, in the future. And perhaps this hypothetical 2-person mission to Mars is really just a flyby for fun, really. I mean, it's not exploration, but it's adventure. And they don't have to be profitable, but they sure can be carried out by private initiative because they can take chances. Now, so all those approaches are needed. However, I doubt that governments in the near future are going to have sufficient funds to do very much. But however, the government can control regulation. And I should say here by regulation, what I mean here is they can open doors. They can make things possible. We've seen changes in regulations that allowed private space to develop in the last decade. And by here I mean not just the American federal government, but I mean state governments as well, where New Mexico has incentivized the construction of a spaceport, and also other governments, other countries in other governments, and international regulation as well, international bodies. Governments are clearly quite stretched to go beyond low Earth orbit and scientific probes, as they have for decades. And they will continue to do that, but I think the larger future we're thinking about is going to have to involve the private sector a great deal. And I think the private companies are going to probably take the leadership role in the rest of this century. That is because there are sufficient private funds becoming available in the hands of entrepreneurs who make things happen without the complex infighting in government, which we all know occurs. For example, the conflict in Washington about the asteroid mission and what it should be like, the continuing struggles about whether we should go to human presence should go to the moon or we should really be heading toward Mars, which is part of what the asteroid thing is about. The commercial actions will be much more focused and practical, like planetary resources, and will probably go faster because it's more focused. An example of that is the comparatively rapid development of SpaceX into the Falcon series. That's really quite something and a model for the future. Historical fact supports an infrastructure follows entrepreneurship model in the development, as though in the development of the canals, the railroads, the highways, and the airplanes in the United States.
Thank you, Jim.
Okay. Well, as Jim mentioned, and I'll expand on, there are at least three flavors of government when I hear this question. There's civil, which funds NASA, there's military space, and there's regulatory. And there's not just one. So when you ask this question, which one do you mean when you refer to government? And that's also true in commercial. What's commercial? There's for-profit, things like the mining companies, deep space industries, planetary resources, the tourism companies, but there are also the insurers. And in the commercial launch business, they're the ones who drive a lot in terms of what gets flown and what doesn't and what vehicle based on past history of the vehicle and what the insurance costs are for the people who are buying the ride to space. All of that comes into play. We're essentially a libertarian kind of group, and that binding any kind of socially normative opinion in this field would be counterproductive. Any answer, if it expresses this norm, suddenly becomes, are you going to tell us it has to be this way versus some other way? I hope not. There is no right answer. There is no wrong answer. We personally believe it's going to be all, some, or none of those options contributing, and that if we decide it's got to be one versus the other, I think we're being essentially counterproductive and prematurely closing doors to ways to open up the space frontier.
So interstellar space exploration clearly requires all of these approaches. Government should seed the activities and help to quantify the risks, develop the initial technologies, and map out the landscapes. The activities and missions should then be handed over to industry, and incentives for industry continuing these activities should be in place. An example of this is the US government support companies like Space Exploration Technologies Corporation, who have received hundreds of millions of dollars of taxpayers' money. These are massive costs because it relates to the commercialization of access to Earth orbit. However, in the future, for small payload missions to the edge of our solar system and beyond, it seems practicable or imminently feasible for governments to initiate global competitions and contracts focused on these goals, which push the boundaries of our knowledge and technology as a form of stretch goal. In addition, mutual support between government, commercial, and private non-profit ventures is vastly more creative than programs undertaken by one type of institution alone. This is demonstrated by the history of global exploration over the past half millennium. This hybrid leadership is critical for the participation and inclusion of the civil community. The hybrid combination of government and commercial and private leadership is also a rich foundation for the initial efforts of an interstellar journey, whilst also allowing for wide-scale participation and inclusion. In summary, we believe it's a creative synergy of government, intergovernmental, commercial, and private non-profit ventures all in parallel.
Okay, I don't have an answer that fits all occasions. I'll just tell you about the tactic that we were using. Again, it comes down to today. What can we do today? And when realizing that actualization of real interstellar flight at best is decades, if not centuries away, and venture capitalists want to return on 3 to 5 years, it's like, okay, we were going to go after philanthropy. Regarding government, I consider the DARPA thing a fluke. As just an odd thing that kind of happened out of the blue. And so 500K to the 100-year Starship, 500K to Space Gambit, and the rest of these organizations are basically operating on an order of magnitude less than that. So, you know, do what we can. So we were going to target philanthropists, realizing that this is such a long-term thing. It has to be people that don't want to eat a quick turn on investment. But that doesn't preclude that if in the course of doing things you get a cool spin-off, that you couldn't turn that on to something. The other thing that kind of bothers me when it comes to, what great plan can we do to get great bucks is that, that's what the Moon Mars people have been doing for many decades, if not a half century, of arguing amongst themselves, oh, my plan's better, your plan's better, or whatever. What good plan can we all think of that would be so great that we'll finally get those big bucks to enable it when that big bucks aren't there in the first place? So again, it comes to, if we want to be wise about how to use our resources and how to find them, at least today, we have to aim on what we have to work with today. Thank you.
Would our deep space capabilities be better facilitated by government or commercial leadership? Now, facilitate means to make an action or process easier. And I'm not convinced, in fact, I'm dubious, that government can execute in a way that's considered easy. So I want to recognize first that almost all the money that's been invested in space since the dawn of the space age, about $750 billion, I want to recognize that that has come from governments, which have a relative abundance of resources when compared to individuals or companies. However, I believe that fundamentally, private enterprise is better suited to the execution. And I think there's a very salient press release that came out from SpaceX, and they articulated that for less than the cost of the Ares 1 mobile service tower, that they had actually developed all the flight hardware for the Falcon 9 orbital rocket, the Dragon spacecraft, as well as 3 launch sites. And that to me is irrevocable evidence of the capacity for private enterprise to execute. With that said, I do believe that governments could play a role in the facilitation of the funding. Perhaps they could do some of the fundamental research that doesn't have a short-term ROI for investors, but my position on this is that private enterprise is swifter, that they're more cost-effective, and not subjected to the changing fortunes of the capricious whims of government elections. Thank you.
I'm going to keep my own watch this time. All right. Couple of things. I'm going to respond to some of my colleagues' comments. First of all, there is a lot of big bucks. There's so much money being invented every minute. You cannot believe how much. Banks create money every day. The Federal Reserve is injecting 85 billion a month since last September. And I'm going to talk about this tomorrow in my talk. There is a lot of money being invented and created every day, so there is money out there, one. Second, government is definitely a source of waste. I totally agree with Richard. I think a lot of things can be done a lot faster if commercial and private logic is applied to implementation. But it's not we don't need government for the funding, though. I don't think governments are abundant at all. In fact, governments are far worse than we are. It's just that we falsely put our hopes on the governments. That's the difference. They're not more abundant. What we need is not just governments and commercial enterprises. We need a triangle. We need the government, the Federal Reserve, and the commercial space industry. The Federal Reserve can, by injecting $40 billion next September, and we have the product, by the way, we have designed the financial instrument as valid as the mortgage-backed securities they're using to put 85 every month in the banks. We have another instrument called public capitalization notes that they can use this September to put 40 billion in NASA's pockets. If you and all of us get together and argue for this type of injection, then we will be able to move this thing now without begging, without asking for help, and without thinking that actually the solution for the money comes from the government. The government is not the source of money. The government is the source of the debt that creates the money by the Federal Reserve. And that's why there's a $16 trillion debt hanging all of our heads while we're going to interstellar space. And I wonder who's going to pay our mortgages once we're out there, because they're not going to waive it from us. And so the bank and the bankers are the third element of the triangle we need to make this an interstellar civilization. Without the banks and without opening their minds and their frequency to what is being said here, I'm afraid governments won't be much help.
I'm going to sell my house.
229.
I'm not sure that I have any greater insight than any of you in the audience on this, but I'm going to tell you what I think. The question is interesting. We must distinguish between partnership and leadership. If you are a scientist or an inventor out here and you have an idea, but then you get funding from the government, who is leading? What is the leadership? So the question is government or commercial leadership or both. I love companies like SpaceX, but even companies like SpaceX right now do depend on government funding for some of their launches and development costs. So it's not a very clear-cut line separate. I personally have things for starships that I've been inventing and developing, and some of it is funded by the government. Leadership to go to the stars requires vision and latitude that's not always shown by the government. So I don't want to be too disrespectful to people that might fund some of my stuff, but to be honest, I have to say, we all know that there is a lack of vision in our society and a lack of leadership in technology development. There's a lack of basic science research that leads to the kinds of discoveries that we're all going to depend on for our dreams. So my short answer is first hybrid, to get things going a bit, and then clearly more efficient private organizations after businesses become more developed and there's more of an infrastructure to support the technological developments we need. So I don't think it's an either or, and I don't think it's exactly a hybrid. I think it's the answer depends on what moment in time you look at it.
So again, this time I heard some specifically very different views. So let me throw it open. So we've only got 5 minutes for discussion, so let's keep the questions a little bit short, so we've got lots of time for more questions.
I'm young, I'm ignorant, and I'm nervous, so bear with me. But we've just gone over talking about economy, and on here now we're talking about space tourism and things like that. And there are so many people with the dream of going to space, so many people in the world, and it's that's just pretty obvious. But all those people think they might never go to space unless it gets cheaper because they know it costs a lot of money to go to space. So a possible way to capture the people's attention and actually get money out of them and to not even need a return on investment would be people throw money away all the time on the lottery and they never really expect anything out of it. So if there was a grand scale space lottery, people might really want to throw money into it if they could possibly go into space. And it could be like halfway Kickstarter, halfway lottery, where it would only happen if it raised a reasonable amount of money, but people would love to just throw in maybe $2, $5 if they could potentially wind up in space in some capacity, and that might be a reasonable idea. People would talk about it.
I love that.
Thank you. Anybody on the panel want to comment on that?
My concern with that model is that it's capitalizing and somewhat taking advantage of people's dreams. It's kind of like that show, American Idol, and you only see the end result, the happy person who the judges, gives them the recording contract or whatever. But behind that is a wake of disappointment, tens of thousands of disappointed dreams. So my only concern and reservation with that, I think it's good to explore alternative models, but my concern is that that's not going to really allow a broad swath of the population to ever actually realize their dreams.
What then do you think are the appropriate near-term goals that ought to be pursued that would be broadly enabling to the precursor stage that makes interstellar travel more credible? So some of the goals being pursued for exploration versus development may or may not be more broadly enabling in any kind of government programs. So what ought to be near-term goals that create the capabilities in space that would really make the difference? And what are the right and the wrong goals that you see right now?
My first reaction to that is, yeah, a lot of the things that, you know, having the in-space infrastructure secured before we can go up for the big things, yeah, that has to, if that has to happen first, that's some time-consuming thing. So in the meantime, what are the things that are affordable and uniquely address interstellar flight are those things that the other people aren't willing to look at, the game-changing propulsion physics things and stuff like that at a small level of research. And to better understand the interstellar problems, mission vehicle studies at a level of detail where they can be accurately priced to really do the sanity check. Well, where do we stand to those? And those can be probably broken into reasonably sized research packages.
All right, thanks, Albert. I think each one of us would have 5 top things on our list, depending what our favorite tech is. If you want one thing, and it's not a business answer, I would say in-situ resource utilization, development of technologies and missions for that. And that's very much the key to developing a nearer term, shorter distance space economy, I think.
Well, what's the timeline? I'm gonna give you an example of what we can do from now until October 16th, 2013, which is the deadline of the RFP offer issued by NASA and GSA for Hangar 1 and 90,000 square foot in the middle of Moffett Field, Silicon Valley. What we can do is we can all get together and bid for the hangar, win the hangar, and transform it into a Starship workshop, get the Federal Reserve to fund it with $40 billion injection, and get this country back on track. That's what we can do from now until the 16th of October. That's the deadline of the submission.
Yeah, one thing I think we've missed is an opportunity to capture a big bit of support, and that's to become relevant, darn it. I think we need to be looking at what we can do in the near term to help solve energy and environment problems on the planet. Whether you agree that there's human-induced global climate change or not, we need to be better stewards. Space gives us opportunities to take certain things off planet, like power generation, space solar power, resource mining asteroids. We ought to incentivize that. We ought to encourage that. And when we go out and we can, are asked the question of what's space done for me lately by the average person on the street, and we point to that link of bright lights flying over the equator and point out the green energy coming from space, and we're no longer strip mining the beautiful mountains of Kentucky, Tennessee, and West Virginia, not to mention Africa for our mineral resources, then we've done something, we're relevant, and we can start taking those steps to the stars. I believe that passionately. That's where we ought to go.
So I think when you're thinking about this problem, you have to distinguish robotic from human exploration for a start. So robots are doing fantastic job out in the solar system, and we've got New Horizons arriving at Pluto in 2015, Cassini sending back pictures of the Earth all the way from Saturn. The robotic space exploration program has been tremendously successful, and there's no reason to think that won't continue, especially with the continued miniaturization of electronics, the development of nanotechnology, and all these things that are coming on stream, 3D printing. Human space exploration is much slower. We went to the moon for geopolitical reasons, not for scientific reasons, and that's also why we stopped going there. It's now 2013, and we still haven't got out of Earth orbit. So if you extrapolate those into the future, we're not getting to the stars, humans, for a very long time, and that's very disappointing. And so, to me, this is my personal view, but the near-term goal, I think, of our civilization should be simply the colonization of Mars. I think if you can crack Mars, and you learn how to build your in-space propulsion capability, whether it's solar cells or nuclear thermal rockets, you start to develop those technologies as a stretch goal. You develop your space habitats so people can live in artificial environments in space as well as on the surface of Mars. You start to build up your infrastructure. If we can't crack Mars, forget colonization of the stars. It's just fantasy. So I personally believe that Mars should be one of our near-term goals for humans anyway. But the robots will clearly get to the stars much sooner, and there's no reason to think that robots can't be launched at this century towards the stars, and I believe the calculations show that they can be.
Why do you favor Mars over an asteroid?
So an asteroid is interesting in terms of resource utilization, in terms of demonstrating capability, continuing that capability of the future. But it really, it's not a very large gravitational well, so you're limited in the capability that you're building up. And you're limited in terms of your space infrastructure and what you can actually put in place. If you want to put humans on the surface, boots on the ground, you need a large planetary body. However, there is an argument that in the future, that human beings will in fact not necessarily be dependent upon planetary atmospheres. And in fact, we will build these huge world ships and so forth, the Gerard O'Neill type cylinders with propulsion engines at the back of them, and we move off into the stars. And in fact, planetary bodies will be mere resource utilizations that we can use, but also objects of entertainment that we can visit. And some people believe we'd actually prefer to live in space, in which case it becomes not so relevant. But I think Mars is just an interesting test of the human character and our ability to solve the problems that we clearly need to solve technologically. And those technologies also have spin-off applications to help improve the conditions back on Earth.
Can I add a small thing on this, since mine was short?
Yeah, to answer directly to your question, I think on a smaller scale than colonizing Mars, nothing wrong with that, but in order to do so, there are two problems that have to be addressed that NASA's consistently neglected, I think. One is to be able, this is for human spaceflight, we need to have artificial gravity in the sense of centripetal force, rotating spacecraft. We think we know how to do that, but we're not doing anything to develop it, and it really would help an awful lot. It's not be good when first people arrive on Mars and they can't stand up. It's something we've got to solve. It's a back burner question that really ought to move forward, because we're not going to move forward without solving it. The second thing is closed ecosystem. You need that in low Earth orbit, you need it on long travels, and you need it on the surface of Mars. So we really have to figure out how to do that. And I would point out that it's really a lot harder than people thought it was. You need to bring the whole, practically the whole microscopic bacterial ecosystem with you to make sure you've got a closed system.
That's a great point. And I certainly didn't put my ISRU comment as eloquently as Les did. But the one thing I wanted to add was the complete opposite. And one thing that people look at, but it's perhaps I think the biggest problem in long journeys, is radiation. And we don't talk about this a lot, and we rehash old ideas from 50 years ago on electric or magnetic shielding, things like that. So I'm going to add to my ISRU comment. We need to look at this radiation problem a lot more carefully if we're really serious about doing this. And of course, going to Mars, if you've looked the radiation thing, I mean, that's part of it. So.
Thank you. So we're going to go ahead and move on to the next question. So this is a good one to close this session with. So this is about the interstellar community, which is all of us. Over the last few years, several organizations have been created which are dedicated to the problems of interstellar flight, each having their own mission statement, strategy, and independent ownership. Would an interstellar mission by the end of the current century be made more probable by these organizations working cooperatively together for mutual benefit and advantage, by friendly competition, or by unifying all support behind a single project? Jim?
Certainly not a single project. Why? Because we don't have an obvious project in mind. We should remember that involving multi-institutional agreement, it's very hard to come to agreement when you don't have a really clear direction. Multiple expeditions and approaches were used to explore and develop North America because it's a big place. And they did it for many differing reasons. That's okay. We're not likely to have a single objective until a lot more research is done. But more likely, we will never have a single objective. Certainly, matters should be cooperative to the extent that it is advantageous to all parties. And that will happen only when the self-interest of the organizations drive them to do such. There will always be an element of competition friendly competition, unfriendly competition, because in a time of scarce resources, and that will always be true in Interstellar, there will be competition for those funds. There already is. There are many personality types currently in this, this community, although you don't see a lot of non-uniformity on this panel, I'm afraid. And we can expect some collisions between these types, especially when there's money on the table, as happens in all human organizations and all of human history.
I'll be brief because I have to agree with, and we have to agree as an organization with a lot of what Jim just said. We believe that the idea of an interstellar community, that it should have a single or unified voice, is both unrealistic and undesirable. There's plenty of room in this ecology, thought, and research space right now for all these organizations and then some. Not only is it premature to unify, but it's not premature to coordinate, it's not premature to communicate, and where it makes sense, collaborate. But I don't see that we have an absolute necessity to unify on any particular project. I think collaborate where it makes sense, compete where it makes sense, and keep the thought space open because there's a lot to be done.
So it's interesting that our view pretty much agrees with the previous two speakers. So the Interstellar Challenge covers a broad area of societal issues, including scientific, technological, economic, political, philosophical, and social cultural. This is what the DARPA 100-year Starship project particularly showed us. Although focusing on one specific project would help to motivate progress in that area, it will not have a sufficiently broad scope to address all of these issues, which is a clear requirement for the establishment of an aspiring interstellar society. In addition, it would likely lead to the polarization of viewpoints and positions without a clear consensus for stakeholder support in place. It is clear, therefore, that a multi-dimensional approach to the problem is required, which sees a wide variation in projects, activities, and missions being pursued in parallel. This will foster progress across the option solution space, but also enable both cooperation and competition at various points. The achievement of interstellar flight requires evolutionary, revolutionary, and disruptive technologies on various scales. Although stability in any specific project or activity is required, stability on the global strategy to see these breakthroughs would not actually lead to the results that we would see, and the risk of stagnation will be great. There is also the risk that too rigid a strategic and technological roadmap will not allow for the inclusion of breakthrough advances to advance the subject. Therefore, there is a clear requirement for the occasional disruptive influence on the global community, or strategies in order to shake things up, create nexus points, and create opportunities for alliance swapping and competition. This will ensure that stagnation does not occur, and also that unpredicted developments can be assured. So the problem requires a multi-dimensional approach featuring elements of both friendly competition and cooperation. But too much competition is wasteful, too much collaboration leads to stagnation. We believe that the growth of a civilization to date, both on Earth now and in space, demonstrates that a creative tension, which contains both elements of cooperation and competition, is the most productive way forward. In summary, the mixture of competition and cooperation characteristic of a free democratic society.
I guess when I think about it is, what would be the ideal thing to do and how it might really pan out, and then responding to that is what I was thinking about. If any one of our groups got some substantial amount of funding, we'd probably use it as we saw fit. If it was Jim, it'd probably be beam sales. If it was Armin, he'd buy a hangar at Ames. Kelvin would buy an institute building. And at this point, I'm not sure how to deal with it. I know that our plans were that we were trying to support small little increments of tasks spread out by getting a system of prioritization of criteria worked out, and then just dole out small amounts every other year, and from the learning on that, and also try and cover subjects that haven't really been brought up that much, like sociology and things like that, which are important. I want to come back to the one about what Les said about making things relevant and overlaps with the hackerspace. And when you think about something that's relevant, that if viewed in the context of exclusively interstellar flight, a closed-loop, life support, sustainable, long-term society, I mean, if you could figure that out, that certainly, and the interstellar goal pushes those challenges beyond just extrapolations of what we know how to do or making temporary bases on Moon and Mars, but it pushes it to a seriously level. Successes at that level would certainly have application on Earth. And if I'm not even going to bother to explain that, because if you don't get something that obvious, I'm not sure what to do. But anyway, you know, as far as what to do as a community, at this point, you know, each of us finding what support we can and chipping away on things as we see fit. But if there was huge money on this, I'm not really sure what would be a realistic way to go forward cleanly.
There's a 1,000-year-old Chinese proverb that says it's the nature of things that are divided to unite and the nature of things that are united to divide. I think that if that indeed is the case, then if indeed it is a question of at some point that which is divided will become united, the next question is, well, when? And I think it's certainly true that it's far too premature to start talking about unification at this early stage. I don't think the organizations and the people fully understand what the organizations stand for, who are the people, and what are their modus operandi. And so I think it's fundamentally a mistake at this early stage in the game. I also think it would be nothing short of a profound mistake to unify support behind a singular project, which tend to become money sinks and suffocate alternative ideas. Now, I think it's true that competition provides motivation for innovation and ultimately success. That said, what can we do now? And I think that a degree of cooperation between the certain organizations, between the right organizations, can be fruitful. A couple of examples. Icarus Interstellar has had a positive and fruitful relationship with Centauri Dreams, which is the news outlet of the Tau Zero Foundation. We provide a lot of articles, a lot of discussion with Paul Gilster, and I think that's a positive and fruitful relationship. A more recent one is our announcement to pledge support of the $500 cash prize of the Alpha Centauri Prize, which is an I4IS initiative. So I think it's taking these small tentative steps and learning if and how we want to collaborate with each other. But I don't think that there's a one-size-fits-all. I think cooperation could work, but it shouldn't be our fundamental modus operandi.
Well, obviously, merging or unifying organizations simply because they all aim to make interstellar travel a reality isn't necessarily the right corporate strategy. I mean, it may for some groups, in other cases it's not. This is an individual organizational decision. But I'm absolutely convinced that if we do not unify all of us behind the project of getting interstellar travel funded by serious sources like the Federal Reserve, if we don't unify our efforts to create to at least prioritize interstellar travel from a monetary sense as well as from a synergy sense and the creation of the collaborative platform, I think we will be making a very big mistake. And I do not think it's about unifying technological avenues. I'm not a technician myself. I don't understand much. I'm a financial economist. But in my view, allow the competition to happen between the ideas of how we're going to get this done, yes. And the technologies that prevail will be the ones that are the most ingenious, the most creative, the most efficient, and provide the maximum welfare to us. But the fact that we have to unite our efforts to make interstellar travel an agenda for humanity, for the US government, for the Federal Reserve, I have absolutely no doubt. And I think we would make a big mistake if we don't put shoulder to shoulder in making sure that this happens. And I wouldn't actually buy a hangar, Mark. Sorry, that's a very good point. I'm not hangar dependent at all. I actually want to create the International Space Development Hub anywhere I actually can. But the idea is that if you build an innovation powerhouse, where would you want to have it? Don't you want to have it on the? Don't you? I would like to have that center very close to the technological a hub like Silicon Valley, or a place where you have the headquarters of some of the most powerful technological innovative companies that are actually pretty much the nervous system of the planet. I mean, PayPal Galactic is maybe one. They should be invited to some of these events. They have just recently announced that they want to make sure that the astronauts pay their credit card bills on time. You know, it's like, don't be late. You know, your mortgages, you use your PayPal. You can use it via the International Space Station and make sure that you respect the democratic debt society. Please, let's be very precise. Let's be very honest about where we are, how much we can afford, and I would actually, just for the sake of exercise, if you don't mind, I would like to see how many of you don't have mortgages or credit cards.
That's quite a lot.
That's impressive, actually. Almost 10%. 5? No. 20? I would say 10. All right, 15%. I mean, the structure of the society, and my time is up, sorry. Yes.
You saw her coming.
Okay, so there's an odd dichotomy here. So I'm going to pretend for a moment to be enlightened and tell you that some of my colleagues know me for helping them with proposals even when we're competing for funds, which seems like a very stupid thing to do. But instead of looking at advanced technology like starships, let's look at cavemen for a moment. So here's my philosophy on this. The cave is deep in our heart, and resources do breed competition, and people would fight and kill to eat and to live. But then there was a time when people realized if they got together, several of them together, they could take down a mastodon, and then everybody could eat, at least if they were part of that tribe. So it wasn't full enlightenment, but it was a group of people that could eat by cooperating together. So I call this the mastodon cooperation. I'm hopeful of things for this reason. I think that people are capable of this enlightenment and mastodon cooperation. I have no illusion with limited resources this will not always happen. Absolutely, diversity is very important. You cannot have everything under one organization. Should we all be attempting to work together? This is the whole basis of what a number of us are talking about on stage and what we've been trying to do. Will we be able to do it successfully? Have all the groups that are members of the community done this? Absolutely not. Have some of the groups shared their resources? Some not, some have. Some of the group projects are about distributing resources in this community. And so I guess I'm going to be naive and crystally like they are on my hippie friends on Maui and go, I'm hopeful for a mastodon cooperation here, but I'm not expecting that to be a pure cooperation effort. Which would be best? I think you need some diversity in your organizations, working together and independent projects done more efficiently that way.
Go ahead, Mark.
Yeah. I have a question for a short answer of everyone here to kind of scale the problem. If you could get what budget for as you could vision what you could use usefully for the next 2 years, what would that amount be? Just for your parochial interest to apply it the way that you would want to. What would that amount be?
$1 million. $1 million.
Okay, Ben, Jim said $1 million.
No answer.
Okay.
I don't know.
I'm thinking for your own organization, for the kind of the way you're thinking, what level of dollar investment would you need for the next 2 years? And for 2 years,
So,
it's just to...
Mark, I'm going to stop you right there. I think that's a really interesting question to throw out. So I think that's a very interesting question to throw out, but let's leave it as a rhetorical question, and because not everybody may want to answer that up front without having given it any thought, or so let's just leave that there. It is an interesting way to think about things. Let me throw it to the audience, and somebody who hasn't asked a question yet, and all the way in the back, lady in the white shirt.
no, solving those problems makes it possible. The question was, if we were to deal with artificial gravity and closed ecosystems and the radiation problem on the way to Mars, which is, I think, are all, that's tractable. The first and third are tractable. It would not make a Mars expedition inevitable or provide the funding for it, because that's a separable question. As long as those roadblocks or stumbling blocks are in the way, we're further away from doing it. We're a technical community. We ought to advocate solving the technical problems for sure. The money problem, we're discussing a lot today, is a bigger problem and kind of outside our expertise, if you don't mind me saying that.
In the green shirt.
The second problem is if you want interstellar competition to succeed, I think you have to support the conventional space colonization and development so you have an infrastructure for it.
Andreas?
Andreas. I'm afraid by standing up I'm going to speak for too long.
No, you won't.
No, you won't.
Thank you, Anu.
You got Anu back.
We've heard about joining together to work on a singular project. We've looked at ways that we could work together. We've thought of what different positions and the different perspectives that we each have. Incentivizing the research, deciding what goal comes first, figuring out how to work together, and all working towards a single goal. There's a solution, proposed solution, okay? A decadal interstellar study, interstellar decadal study. We collaborate on defining what the goals are, like NASA does for the next 10 years, as an interstellar organization for all of interstellar research. That gives us a set of projects, not a single project, to work together, because we already have a project that we're working together and it's on our wrists. It's to build a Starship. And building a Starship means working on all of the other things until we figure out exactly how, circling down and figuring out the problem. Now the next thing is, how do we do this? How do we do this and produce financially self-sufficient sort of research engine and production engine? Well, the National Science Foundation, the Department of Energy, and the military have been doing this for many years. It's with SBIR grants, small business innovation grants. Something that we've been discussing with Icarus Interstellar for quite a while now is a small business interstellar innovation research grant. So if we have an innovation platform that is tied to the decadal studies, then people are working on building businesses on innovations that are relating to the decadal study. And that's one of the hardest things of doing an SBIR, and I know that many of the researchers here have been in this kind of situation, that you as a researcher are tasked to figure out how to make this self-sustainable and how to profit in order for this to be something that can sustain you in what you
Thank you, Andreas. Let's turn that over to the panel for any comments. Briefly, please, Kevin.
So I think it's an excellent suggestion. I think the idea of many organizations working together on a particular project like a decadal study is a good idea, heliosphere probe, stuff like that, provided it doesn't mean the organizations have to dedicate all of their resources, all of their personnel to that one specific project, because every organization has its own mission statement and its own strategy, and so you have to make sure you're covering those broad areas. But I think the idea of lots of organizations cooperating on a particular project, provided it's not an exclusion of doing all the other things, is a good way to bring people together and to move forward on the global agenda, because if you've got a Voyager probe out there, which we've launched together, and it's sending signals back of a dwarf planet, way outside Pluto, or even a brown dwarf, that's a pretty spectacular achievement, which is bound to inspire the entire world, and there's no reason why we shouldn't do that.
Anyone else on the panel?
Yeah, I think it's a wonderful idea, and good ideas are a dime a dozen. And so, but it's a very good one. And I would contribute. And so I put it back on you since you stood up. Could you not start something like this, a large, maybe a small project, open source project, a project with people here, to start hash out some framework for that? Can you do that? Would you do that? Just don't answer. But I think it's a great idea. It's all about any of us stepping up. I know you're doing a lot of other things too. So yeah, I like it. Would I help? Yes. Can you do it?
Anyone else on the panel?
Yes, Andreas. I think that's a very good idea. That's a very good slogan. You ought to copyright it, SBIIR, or something like that. And maybe I'll think about doing that.
So one last question before we close out the evening.
So I have a question and a comment. 100 years from now may be like 100 years previous to now. And so when you think ahead of building a Starship, as has been often called the case here, and you look ahead 100 years and you say, what is 100 years from now going to be like? Is it going to be like we're talking about today? Is the technology going to be relevant today? If you go back 100 years to the year 1913, and you ask yourself, what was technology like? How were people dreaming of going to the moon and to other places? And you say, we were on a panel 100 years ago. You're discussing how to get to the moon. Would you have been speaking of the relevant technologies? Would you have been speaking of the relevant organizational skills to get there? And I think the answer is an obvious no. Now, it's not that we shouldn't do this. We should do this. We should do exactly what we're doing because we have nothing else to do along this path. But I think it's incredibly important not to be so naive as to expect that we know what's going to happen in the future any more than 100 years ago. We were naive to expect what would happen 100 years hence. And I think it's incredibly important because it's very easy to be very now-centric. The other comment I have is that unfortunately our space program has been treated like a political football. And anybody within NASA, I think, can attest to that. I'm sure Les has some comments on that. But he won't, I know, because you can't. You can't, I know, but it's in your eyes, Les. We all know it. We all know it. And part of the problem, I think, is, every couple of years, are we going to the moon? Are we going to Mars? Are we going to an asteroid? Are we going to send robots to an asteroid, people to asteroids? What are we going to do? And you know what? I'll put money on the table that 4 years from now, it's going to be something else. Why? Because our space program is very politicized. And that's unfortunate. The way that decadal reviews work is people get together. Why? Because there's a vested interest in the decadal report pulling in funding. There is an incentive to do so. The decadal reports are not written for fun. They're written for funding. And there is a difference between fun and funding. There is a D at the end, and then an ing. And in order to get there, in order to have a credible decadal report, you need to have a credible funding agency to which you're submitting it. And I just would urge some discussion of that.
So that takes us to the end of the session. We're out of time. Jim, you can have 20 seconds.
Okay, I wanted to say that what you should, senior advice, do a lot of networking at this meeting. That's what these meetings are really for. We're still individuals, not organizations. And an example, I just realized I'm doing that. Tonight, I've arranged for 8 of us who are interested in developing beam-driven sails. We're going to have dinner together, and we're going to work on an agenda of how to push that forward. I didn't tell the other guys that there's an agenda at dinner.
Now we know.
Now you know.
So, thank you. So that
It's
takes
dinner
us to
time.
the end of the first General Assembly session. We will meet again tomorrow, same time, 3 more questions. Let me encourage all of you to take a look at the program. Opposite tomorrow's schedule are the 3 questions, so you can see, you can formulate some questions in advance. I want to thank all of you for staying, for participating, for asking some really good questions. I want to thank the panelists for today's questions, and looking forward to doing this again tomorrow.
Thank you, Honored.
Do you have a reservation, or we just show up?
We have a reservation. We do. We have the best table in the restaurant.
Is the 8 p.m. session here?
I'll take it.
And we need to put this in.
You're obviously a perfectionist. Obsessive compulsive.
I'll go up there. Hold on. I'm going to go down to yeah, and then I can, if I need, I can flag you if I copy. Yeah, I'll give you. I'll try to ping you. Like I'll try to do this when it's on question time. So when I do that, I'll leave my hand up until I'm pretty sure you're doing it.
I'm just going to sit right back there. Something here from the So I'm not from the Maui Institute.
Test.
I don't think there's anything to do with you.
Yeah, just on this one, yeah. The other is fantastic.
Okay, I haven't. You're not?
What I went back to is stuff between like 8.
How did I? You know what? I bet in 2011 were you? I don't know where it came from. I'm very sorry. Sadly, it's a PDF and I can't correct it. I feel really bad. So repeat it. Repeat. Okay, I might have you repeat that again. Hold on. University.
Advanced Technology Research Center.
Well, let's just say a function of
Hey, Heath, you're 10 minutes behind you. I apologize.
Yeah. I'm just going to say that part and apologize.
Don't apologize.
Well, you know.
Close enough. I thought it was
Hawaii was the two first ones.
Doesn't matter.
Yeah, University of Hawaii. That's good. Good evening. We're running just a few minutes behind, so we should probably go ahead and get started here. Thank you all for being here. And I will say I'm gonna have to stand at the podium, and all you guys have bravely been extemporaneizing with the microphones, and I have too many particular things I need to say. So sadly, I'm going to be reading from a dull script both today and tomorrow. So you can lord it over me on that count. And thanks for being here. Before we get started, I want to take a quick poll. Raise your hand if you were present at the DARPA 2011 Public Symposium. Impressive. Now, raise your hands if you wanted to be there but were not able to. All right. Well, in a way, this session is for the first group of you to celebrate the impact of an event that you experienced firsthand. But it's also for the rest of us, people like myself who were not able to be there, but really wish they could have been. I was aware of it too late, but I did realize that one of the most inspiring and interesting things about it was the idea that anyone could participate in DARPA 2011 and represent their ideas in that forum. So by career and calling, I'm a librarian working with at-risk youth on technology literacy. Over and over, I have seen the positive impact that including someone not used to being included can have. Opportunity can completely reshape a person's future trajectory. In my session tomorrow, X-Risk 101, I'll be updating on the Vessel project, an approach to long-term archival that only came together because I was able to see it in the light of a long-term goal like securing an interstellar future for humanity. I've seen firsthand the amazing impact that such an idea can have on all your prior ideas, causing them to come together in new combinations. So we're here tonight to celebrate the unique and lasting impact that bringing so many voices to bear on a challenge that cannot be faced alone can have. I was asked to introduce this session as the Outreach and Collaborations Coordinator for Starship Congress, having worked with Icarus Interstellar to bring about the FarMaker Speed Sketch Challenge as well. But I wanted to see Stakeholder Stage happen in particular because of the conversations I had and new friends that I met in 2012. Many of them had been at DARPA 2011 and had seen their trajectory profoundly impacted. All of us were seeking ways to continue building on our shared momentum. The idea of a Starship Congress has the potential to spark unexpected chain reactions and positive feedback loops among its participants. I'm not a rocket scientist. I had to use that joke. I'm a futurist librarian. But it seems to me that to spark a chain reaction, you have to have a place where the many different elements you're bringing together can blend and catalyze one another. DARPA 2011 was one such incubator. And that is the aspect of this approach that we hope to honor and evolve here. Some things happen but once. The DARPA 2011 Symposium was one of those, and from its momentum, many things were bound to arise. The lifelong work all stakeholders brought to that table was never likely to dissipate after the event. Like the presenters who raised their hands earlier, like our guests on the stage tonight, Icarus Interstellar's representatives were presenters among many at those proceedings. Now we have an opportunity both to honor the past and to look towards a future beyond it. On its own, the Icarus Interstellar team represents only Icarus Interstellar. But together we can represent our shared commitment to concrete progress towards an interstellar future, where Earth, this pale blue dot that we call home, achieves its full potential. Our master of ceremonies for the Stakeholder stage is Ian O'Neill. Ian is the space producer for Discovery News. In this role, he combines his expertise in solar physics and manned space flight with his passion for investigating the inner workings of our universe. Ian will introduce our speakers, who will update us on their evolving work since DARPA 2011. And like a kind of a systems check, we'll take stock of our status before setting our sights once again on the horizon and giving everything we've got to reaching it together. Ladies and gentlemen, Stakeholder stage.
Thank you, Heath. As Heath said, I work for Discovery News, and it was kind of a strange manner by which I fell into interstellar subjects. And I'm very proud to be here today and be invited to do the Stakeholder stage and just to be involved in this amazing event, the first Starship Congress. So I kind of got involved with interstellar studies because, as he said, my background's in solar physics. So why would I have made that leap into interstellar space? It was back in 2009, I believe, and I'd written an article about this guy who'd written some science about the warp drive, because I'm a big fan of Star Trek. And I think I got his name wrong in my article, and I had a phone call, and I thought, God, you know, what's this guy calling me about? And it turned out to be Richard Abusi. Looking at the name, I thought he was French. He certainly wasn't. He was from my homeland. So we instantly hit it off. And then from that day forward, he just sent me some articles saying, okay, this is what Icarus, well, at the time, Project Icarus, this is what we're doing. It's a 5-year study into this interstellar probe, and it gets its inspiration from Project Daedalus. And I was just blown away. There was this community that I'd never really come across in my field. And being a space producer, I kind of wanted to bring this to my readers. So we worked on several guest articles from the Icarus community, and many of them are here. And it was just wonderful just to have their voice on our website, and it turned out to be the most impressive articles. The writing was high caliber. We had fantastic artwork by Adrian Mann, and that just really communicated the interstellar dream. And our readers responded very positively. We had a massive interest, and everybody hung off every single Icarus article that came. And there was a huge series in the end, probably like a dozen, if not 20 articles were on our website. And that's when I was introduced to the interstellar idea. And I went from thinking this is just completely nuts to actually there's something behind this. And that really was embodied in last year's 100-year Starship. I was a track chair there. And I got to meet most of these guys here. And it was a great experience. So I'm very proud to introduce the stakeholders, some key players in interstellar studies. First of all, we got Mark Millis of the Tau Zero Associates, just here. We have Daniel Sheehan of the University of San Diego and Paradigm Energy Research Corp. We have Joe Ritter of University of Hawaii Institute for Astronomy. We have David White, VP of Engineering, Art Research and Development. Hey, that's me. Research and Development at Ike Industries, Inc. And finally, we got Paul Gilster of Centauri Dreams. So first of all, we're going to go to 10 minutes or so of a presentation, and I will open up to each member of the panel to discuss their their background a little bit more, and I invite questions from the audience as well. So I'd like to hand over to Mark Millis.
Forward and backwards.
Okay. Well, we'll get right on to it. One of the things that I thought would be helpful to see is, well, what was going on before the 100-year Starship? On the top there, the British Interplanetary Society, they've been in existence, I was tempted to say in eons, but that's an exaggeration, many decades. And they did cover interstellar topics on occasion and at quite good depth. Meanwhile, when I worked at NASA on the side, I was doing this thing, warp drive wind, to try and answer, well, when it comes to Star Trek, you know, what is the real status there? And that and the effort of some other colleagues led to creating the Interstellar Propulsion Society, the oldest group actually devoted exclusively to interstellar. But when the NASA Breakthrough Propulsion Physics Project and then also Interstellar Precursor mission was doing work done, we let the Interstellar Propulsion Society slide. But from there was some other involvements with a group called Starlab, Case Western, where I got a degree in physics entrepreneurship, which, if it sounds schizophrenic, it is. And then Paul Gilster with the Centauri Dreams, which was like an overview of everything that had been being done interstellar. We all kind of combined our efforts. Okay, well, let's get the society going, and to try and set a foundation of references and defining the problem accurately enough to where we can actually chip away at things. And one of the things that happened shortly thereafter is Project Icarus, when it was just a project, was a joint thing between the British Interplanetary Society and Tau Zero. Oh, and there was also Perigonus, I'm probably terribly mispronouncing it, but that was another one that was started by a guy in Hungary for interstellar things, where he did a lot with human aspects. So anyway, then came the 100-year Starship and a whole profusion of various activities. And amidst those, there have been lots of very divergent people coming up with solutions. So this is my way of doing interstellar flight and stuff like that. And the ones that are on here are really just, it's not even a fraction of the, well, okay, it is a fraction, literally. Not a large fraction of the kind of things that are happening. So, you know, so then it comes to the point about, okay, with all this going on, what can we do today? And because when we were looking at, you know, pace of things, and I've said before, at our current rate of procrastination, it might be 2 centuries before we even have the energy or finances to do it. So what do we do today? And what Tau Zero is doing is trying to understand the problem well enough and find the pioneers to chip away at that. So, you know, in a sense, after watching all the emergence of these various organizations come up, it's like, well, you know, that idea of understanding the problem and trying to keep track of things, and this certainly includes Paul Gilster's Centauri Dreams, which is the news forum for keeping track of anything interstellar. That's kind of the thing that, as a group, we were working on. And as an example of, you know, still trying to help define the problem, and this is one of the things that I was going to present, is how do you convey how fast you need to go to reach certain destinations in certain time frames? And there's actually, well, we have a tutorial on the website now that explains how you read this chart. And all those distances and things like that are actually based on published information that's been peer reviewed. And so it's just kind of interesting. Like if you look at, let's see, does this have a laser? Yes, it does. If you look at, you know, like the human lifespan, or here's the other one, how long we can guarantee equipment might last, which might be pushing it to 2 centuries. So if you want to get anywhere, say like to Alpha Centauri within 2 centuries and ask how fast you have to go, well, it's beyond 100th the speed of light, which isn't too bad. But if you want to ask, you know, how far to get in that range where there might be habitable planets, oh, then you're talking a speed roughly like this, which is roughly half the speed of light. And the other thing that's kind of interesting when you look at this about these various speed curves is every time you go, and these are factors of 10, you go at least a factor of 100 in how much more energy you go. And that's for ideal space drive propulsion, not including propellant. So anyway, doing these sort of things about trying to help convey what's the nature of the problem rather than trying to deselect is something that we're still aiming for. But then on the more personal level, since there's everyone out there with their ideas, and I haven't seen that much on the area, and it was my personal interest too, about the idea, well, how do you conquer gravitation and inertia? And so that's the thing I'm now trying to get more back into doing that rather than trying to do organizational stuff, because a lot of the organizational stuff is nicely being handled by others. Anyway, to kind of explain, okay, what's the deal here? And the disclaimer, this is only intended to illustrate the concept as opposed to that this is a ready-to-go viable idea. But if you have your magical spacecraft there and you turn on your engines, can you push against the surrounding matter? In which case, propel yourself if there's some way to do that. And then you can extend that, well, what if you're talking about all the surrounding matter in the universe rather than something nearby? And if you propel yourself and the universe moves in one direction and you move in the other, if you're familiar with physics, you realize already you've got a conundrum there because, okay, what was the universe's frame of reference that this whole system moved on? And what you get into when you get into the details, there's a lot of unfinished physics about what is an inertial frame, what is inertia, how is gravity really related to the other fundamental forces that is completely unfinished. And by looking at this from the point of view of spaceflight, I hope to discover things that would not otherwise be discovered. So, getting back to the whole nature of what was the impact of the 100-year Starship thing, well, it brought out a whole profusion of ideas, actually, and quite a profusion of organizations. I think there's like 7 or so now, not including folks like SETI and the Planetary Society, or the British Interplanetary Society, but I mean one that we're trying to go for the DARPA funding. So with all that going on, and Paul Gilster still maintaining the Centauri Dreams to keep tabs on what's going on overall, at Tau Zero, we're just kind of letting things coast as they are, still trying to provide the general service of, well, this is the span of issues and activities that are out there without trying to down select on any, and on all those, hope that they can nudge progress along. And then on a more personal level, the effect it had on me is like, well, geez, if there's all those other people willing to do organizations, maybe I'll go back and do the fun stuff. Thank you.
Mark, I just had a question.
Yeah.
So going back to DARPA 2011, what would you say was the main, I mean, having a good overview of, overview understanding in Tau Zero, what was your key development that you can see in the community that's really grown?
The one thing that really surprised me, that when we had been thinking about doing workshops on our own, we were not inclined to open it up to the general public because frankly, we've had some challenges dealing with over-enthusiastic people, trying to think of a euphemistic way of putting that. But and DARPA opened to the public, and I was really impressed by the caliber of the, just if you want to call them fans there, on how much they were already up to speed on things and the level of intelligence of the questions. And also, I was glad to see that DARPA did also include the issues like the humanities and what does this mean as far on a social level and things like that, and opened up the issue of how do we finance those things. So that was opening up things that we had not really been able to even broach very well.
Does anybody have follow-up questions on that? We've got time for a quick question for Mark. Anybody? Okay, we'll get on to our next speaker. It's Daniel Sheehan from the University of San Diego and Paradigm Energy Research Corp.
Good evening. This evening I'd like to talk about some research that's occurred since 2011, which I think will bear on where things are going. All of you understand now that interstellar travel is very energy intensive. If you look at propulsion alone, looking at something like a 1,000-ton spacecraft moving at a tenth the speed of light, it would require roughly the entire world's annual energy production to bring it up to speed. If you were to look at the cruise ship and ship maintenance, it would be about 100,000th of that energy, but still substantial. Much of this energy goes to thermodynamic inefficiency. And what I mean by that is that based on thermodynamics, you can't get all of the energy out of a system that you would want. For instance, one spoonful of food, at least in the United States, requires about 20 spoonfuls of oil to bring it to your mouth, plus a lot of sunlight to grow the grain, and so on. So if you look at the thermodynamic efficiency of just food, it's a fraction of a percent. If one wants to do something like antimatter production for a spacecraft and use one of the most productive means known, which is to use a laser on a gold target to produce positrons, one finds that the thermodynamic efficiency of that is about 1 part in a million, or about 1 millionth, which means that 99.9999% of the energy you put into it ends up as heat, and only 1 part in a million actually turns into positrons. Terribly inefficient. If one looks at nuclear rockets, you have problems with self-heating, where the spacecraft itself gets heated by the reactions. And thermodynamic efficiency of some typical nuclear rocket might be on the order of 1/10, which means that 90% of the energy might be thrown away. All of this arises from what is known as the second law of thermodynamics, which by some people's account is the supreme law of nature, or at least according to Arthur Eddington a century ago. It can be stated in more than a dozen ways. Most of us understand it as the increase in entropy of a system by spontaneous processes. Heat cannot be turned solely into work in a cycle. That's impossible. Heat goes from hot to cold. There are no perfect refrigerators, no perfect heat engines. Nothing's perfect. We all die in the end. Okay, the second law is the most depressing law of nature, but it also has a certain mystique about it. Even to question it has been, for more than a century, been a fool's errand. But that's changed, and most people are not aware of it, but since 1990, more than 30 challenges have entered the refereed scientific literature, challenging the absolute status of this law by more than a dozen research groups around the world. More than 80 articles, a number of conferences, a monograph. Theory, simulation, and now experiments are beginning to demonstrate that the second law is not only violable, but perhaps has already been violated to some degree. In 2011, at the 100-year Starship, I discussed some research done at my university having to do with a solid-state challenge. This dealt with intrinsically biased, what are called NEMS or MEMS, which are nano-electromechanical systems, resonant oscillators. And the idea behind it is that when you put an N and P material together in a geometry, let's say in a horseshoe shape, where you have N region on the left, P region on the right, and then a gap in between the two, you can, in principle, according to analytic theory, generate very intense fields on the order of about 10 to the 7th volts per meter. And the energy density associated with that scales as the electric field squared, which is in fact pressure. So based on that, it seemed possible to create a resonant oscillator, in which case this gap could be closed, discharge, open, recharge, close, discharge, and recharge, which would in effect create an oscillator which would continue to oscillate forever, and from which you could, in theory, extract mechanical or electrical energy. About 2010, we actually built a version of this which did not oscillate, but was simply to check whether that electric field was present. Most experts said it would be impossible to have an electric field there, because if you did, it would allow you to violate the second law. Well, in fact, we measured the electric field in this gap. Here's an N region on the left, P region on the right, built in a form with a gap, and we actually measured the field there to be roughly what you'd expect, dischargeable and rechargeable. So that was the status of things about 2 years ago. Since then, we have changed direction to a type of second law challenge which we had investigated for the last 15 years, which involved gas surface interactions, which have a number of advantages. In these, one has two separate materials. If you look in the diagram on the top left, blue and red correspond to two different surfaces. Each surface could have a different chemical reactivity with respect to a gas, causing the dissociation, reassociation, or recombination of a dimer from monomers. And if that occurs, you have, in the long mean-free path regime, this would allow the transport of chemical energy between the surfaces, which in fact could heat the top surface and cool the lower. The theory about that is written on the right. In the last year, we carried out an experiment to test this, in which we have a vacuum chamber with a black body cavity raised to a temperature of between 1,500 and 2,000 degrees. On the right-hand side is a blow-up of that, in which you have a black body cavity made out of tungsten, and then rhenium tungsten thermocouples inside, coated thermocouples on the inside. When hydrogen gas is passed into the cavity, there's a spontaneous temperature differential created in this black body cavity over 120 degrees. By the laws of thermodynamics, particularly the second law, this is impossible. But this was observed and was repeatable and explainable in terms of standard theory. The power densities associated with this were about 1/10 of a megawatt per square meter. The characteristics of this type of heat recycler, in other words, something that in principle can turn heat cyclically into work. It's mechanically simple. It has high power densities, more than a megawatt per square meter aerial. The experiments demonstrated about 1/10 of that without even trying. It could be optimized. High power to mass ratios in the order of 100 megawatts per kilogram. Ultimately, you're limited not by the device itself, but by how fast you can actually feed working fluid into it to extract the heat. The thermodynamic efficiency almost has no meaning in this case, but should be on the order of 1, and it's scalable. So how would a heat recycler help things? Well, it could take something like antimatter generation and turn it from something that's very inefficient to something that has an efficiency of 1, in which case it would be 1,000,000 times more efficient. Nuclear rockets could be improved in their efficiency by a factor of perhaps 10, and the heating and the bulk heating could be eliminated. Crew and ship maintenance, you could have a sealed cavity or in which your crew could live for 1,000 years, recycling its energy again and again, never needing any new types. Now, the challenges of interstellar travel, the big challenges, have to do with time, space, and energy. Heat recyclers do not solve these problems. They simply don't. These have to be solved by other people. But what heat recyclers do is mitigate the problems. In other words, increase the efficiency of energy production and usage by orders of magnitude. Now, still some would say, well, this is pie in the sky. After all, you're attacking the second law. Well, if you look at what a Starship is, by definition, it's virtually a parade of impossible technologies. Photon rockets, wormholes, cryopreservation of humans, and now heat recyclers. Well, heat recyclers now have a good theoretical basis and experimental verification. So by most measures, they are ahead of most of the other impossible technologies. Thank you.
Okay, does anybody from the panel have any questions? Because I don't want to hug this to myself.
Just a quick one.
Yes.
So is the Carnot efficiency irrelevant, or you really have a Carnot efficiency of 1? Or
well, the Carnot efficiency is kind of meaningless here, because if the heat recycler doesn't get the energy on the first pass and turn it back into work, it'll get it on the next pass. In other words, your heat will, if you stick to it, will eventually all be turned into usable work, in which case your efficiency is effectively 1.
I guess I didn't understand all, but I'm going to talk to you. But thank you.
Okay.
Any questions from the audience? Oh, we got a few. We'll start over there.
Yeah, anytime when someone says efficiency of 1, you are violating the second law.
Well, I didn't make the laws of physics. Well, yeah, but again, I mean, I think you're missing the point, is that in any particular system, let's say the oscillator, sure, in each slap you're going to create some waste heat, but that waste heat simply goes back into the system that can be recovered on the next cycle. Not if you have an adiabatic system, one which is well insulated. That's not true. But you can I'm sorry, you can actually derive the energy from the environment itself. That's the issue. The universe itself is your heat reservoir. In this room, the heat in the room, in the air in this room, if you were to take just the heat energy in the air, it's equivalent to roughly several boxes of TNT. But it can't be exploited because the room is basically isothermal. But if you have a heat recycler, it can essentially sap the heat right out of the environment, whatever it happens to be, and turn it into usable work. That's the point. No, the theory is well established, and the experiments have been done, and laws of physics are all contingent, which means that they're only true insofar as they are observed to be true. There is nothing written in stone in the laws of physics, and to claim so is an epistemological error.
Okay, next question. Just down the front here.
I'm sorry, I couldn't hear that.
Have you ever submit your work to the medical review letters? And if yes, then what was the response from the reviewers?
I think you're asking about the review process, is that right? Okay.
Yeah, if you submit some papers.
The theory behind the heat recyclers, at least in terms of the gas surface one, is right now is in press at Physical Review E, and the experiment is under review right now at Foundations of Physics. That's right.
What is the response for the reviewers?
The reference?
What's the response from the reviewers? What was the response from the reviewers?
The reviewers thought the theory just fine.
Excellent. Back here, blue shirt.
What do you intend to do next, I suppose, and when do you think What do you intend to do next, and when do you think it could be used in a system that you could prove it on, like an engine or something?
Right. The research I'm doing right now is pure research at the university, but it has a dual use, which is, of course, there are an infinite number of uses for turning heat into energy. Paradigm Energy Research, which is my company, is actually trying to commercialize the technology, and we have a couple provisional patents right now on the material.
Okay, final question is a quick one, just behind.
I'm always interested in new ideas, although in the end, a lot of the new ideas turn out to be not. Can you go back to your experimental setup for just a moment, please?
Certainly. Go ahead.
And so the PRL that you're referring to is which?
Sorry, go ahead.
Which review article are you referring to? Which article are you referring to that?
Okay, the article which covers the theory, there are two. One is in Physical Review E from 1998. The most recent one, which is in press, should come out later this year, 2013. The experimental work is in review at Foundations of Physics currently. But there's a great deal of other work done by other researchers that basically back the essential ideas, which you can find throughout the scientific literature over the last 50 years. I mean, they simply haven't put their pieces together on that. It basically has to do with the fact that surfaces of different chemical composition like tungsten, rhenium, molybdenum, tungsten, tantalum, have different chemical reactivities with respect to gases. And as a result of that, if you put two surfaces of different chemical reactivities in proximity, in a long mean-free path regime such that the gas phase equilibrium cannot establish between them, you can have different dissociation and recombination rates on the two metals, which effectively causes a net transport of energy between one surface and the other.
I agree, but you effectively have a battery, and a battery is consumed in the process. How do you know that you're not consuming the consumables in this process, and therefore what you've seen as recycling is not recycling, it's the use of chemical energy it's already stored?
The black body cavity was constructed in such a way that the molecules would undergo roughly between 1,000 and 10,000 collisions before leaving the cavity, and under those circumstances, you could treat it as a black body. Furthermore, the length of time in which the temperature differential was seen was sufficiently long, and the temperature differential was so high, over 120 degrees, that there was no way that these surfaces could have maintained themselves chemically in any way. They would have been dissolved away if they were trying to maintain these high power densities for those lengths of time. So that was not a way of explaining it away either. But on top of that, a number of other experimenters besides me have seen these same effects. In other words, differential chemical dissociations on different surfaces. It's been seen for 100 years, all the way back to Langmuir, about 1910. The difficulty was for them is that they didn't see the connection between that and the second law.
Yeah. Right. I think it'd be good to look at the cold fusion debacle.
This has nothing to do with cold fusion.
I understand, but the whole process by which that came down, anyway, hopefully.
I would welcome somebody to check these results.
Thank you, Daniel. Keep violating that second law. I never liked it. Okay, our next speaker, Joe Ritter from the University of Hawaii Institute for Astronomy.
While they're working on that, I haven't read your paper, so I've got to give benefit of the doubt. And I have to say, I've been accused of writing science fiction, and I always go, I meant it. It was real. And so I'm going to read the paper before I read any comments. Let's see. Okay, 10 minutes. First, I was remiss earlier not on stage in thanking everyone for having me here. And Ian, thank you. And for, I want to call out Richard, but there was a whole organization. Everybody did so much. So I've now wasted 50% of my time on that. But I wanted to say it, and I mean it. And I'm really happy to come to a conference where people came further than I did, which is unusual for this. I went to the 2011 DARPA conference about a week before it. I was sitting with some physicists, and they said, "Oh, you're going with us, aren't you?" And I said, "Nah, I don't think I'll go." And they said, "Oh, no, you need to give us an abstract tonight." And so after 3 glasses of wine, I wrote an abstract, and I'm going to tell you about this. And I got an email from DARPA TTO the next morning saying, "Here's your slot." And so that's, Heath asked me to tell a story about how we made it there, almost didn't make it there. So what has happened since then? I'm just a scientist, but I get involved with all these people going after money and things like that, and we formed organizations, and we did a lot. And so with that, I'm going to give a very quick fire hose talk. From earlier, our greatest tool is teamwork. And I firmly believe this, and this is what I was talking about. We formed a group to propose for the DARPA money. Our group didn't win. We had an interesting cast of players, and we all decided that it would be worth trying to pursue some of these things anyway. We, a year ago, held our first open source space conference. We did this in conjunction with ISU, and down at Florida Institute of Technology, we had about 600 or so people. They had to cut off people walking into the auditorium. We had a couple hundred people online. So that was kind of fun. And it was all about open source stuff, and I'm interested in open source stuff. We've had various team members from many different organizations do things since then. We had some that did some microgravity research on station. I'll shift and put on my Space Gambit hat for a minute. One thing that came out of DARPA 2011 was funding of a proposal, the Global Alliance of Makers Building Interstellar Technology. And what is Space Gambit? It's a global alliance of hackerspaces and aiming to do research to build technology and explore and settle space. And it truly is global. And I don't know if we have all the dots on this map, but it's most of them. This is me out in the middle of nowhere here. But actually, the Maui Makerspace, Space Gambit is headquartered there, actually. Jerry Estelle asked me if I'd come and present some of this tonight. Space Gambit is about researching and building spacefaring technologies and exploring and settling space. Fundamental principles are open source technology, open source hardware, curriculum development, working with students, doing research, real inclusivity and sharing, and international cooperation. Real quick background, because I have too many things tonight. It came from 2011. A proposal was submitted. We received about 50 different projects for funding. We've so far funded 9 of them to the tune of about $130K. We're looking at having a competition. More on that later this year. The current projects are, somebody mentioned closed loop systems earlier, and something hackerspaces could do. Great. And so we have a couple of those. We have some stuff with Boy Scouts. We have basically makerspaces, hackerspaces in a box. Other open bioreactors. I'm working on printing vacuum compatible Pokebots. You know Gumby? He's flat and pokey. So I've got a new 3D printing thing I'm doing. Satellite simulation, spacesuits, hackerspace workshops. I know some of the Icarus gentlemen won some of these. So it's all competitive. And great. So DARPA 2011, what I lectured on was combined imaging, power generation, distribution, propulsion, and communication subsystems. And so I'll wax for a moment on design philosophy. The idea is to have hybrid multifunctional systems, and this is to reduce cost, reduce mass, reduce fuel consumption, reduce building costs, reduce complexity in complex systems, improve utility, give you better capabilities, create redundancy, have multiple systems that can take the place of each other, and mitigate development risk. So also ensuring funding streams. If all of us work on one particular technology, then you go, great, if it's defunded, it's dead. So if you have things that have multiple uses, you might have multiple funding streams. So that's just a little philosophy on it. I'm interested in imaging exoplanets. Tomorrow morning I'm going to give a little talk on nano-arc-second imaging with current technology. So that might be a bizarre pie-in-the-sky thing. That will be science fiction. Maybe not, maybe not. So first example I'm going to give you is a multi-use deployable dish, a large aperture telescopy. I'm working on a project for the NASA Innovative Advanced Concepts program called Optically Controlled and Corrected Active Metamaterial Optics. But if you have a big telescope, you can generate power, you can distribute power, you can beam power, you can do life support, you can do propulsion, you can do communications, you can do materials processing. How do you do all that? Well, step one, first you've got to make these large telescopes. And I'm not going to go into this in great detail, but photons weigh nothing. So why is it that space telescopes weigh tons? Or I'm a physicist, I know no gravity, so let's say have high mass. And the answer is you have to keep the shape of your mirror perfect to a millionth of an inch. And this takes rigid, heavy materials or active materials. As a reminder, here's the not very big Hubble mirror. It's about 300 pounds for every square yard. It's a heavy, monolith, ground-based design. When I was at NASA, I worked on JWST. It's now a $9 billion project. So how do you do all this? Typically, if you were making a mirror, you have a big, thick hunk of glass. If it's X wide, it should be X over 6 thick so it doesn't slump under its own weight. Some basic continuum mechanics for you. If you support it on a couple of spots and you have gravity, let's say you're polishing it on Earth before you launch it, it will slump on these points, and this is given by the Young's modulus of the material, or modulus of elasticity. A lot of engineers in the room here. So I did a small calculation for borosilicate glass with a certain spacing and showed what is an acceptable slump, maybe 25 nanometers for a so-so mirror. And so you can make mirrors thinner if you put actuators on the bottom and control the shape. You can make it even thinner if you have more actuators. So the obvious extremum of the design trade space is to make it infinitely thin with an infinite number of actuators. Laberry wrote a paper in '74 where he talked about doing it with laser beams and molecules. I know somebody made one about that big. It's very difficult. Didn't work very well. But great thing to try. But it turns out there's a sweet spot in the design trade space, and that is something that's about 1,000th of an inch thick where you have every single molecule is an actuator. And so this technology takes a well-known phenomenon called cis-trans photoisomerization, where the shape of a molecule will change when you hit it with light. And so over the last 14 years, I've probably made 100 different materials with people that are much better chemists than I am, and we have made some stuff that you can control and bend with light. This is a new kind of transducer. Everything in the universe is a transducer. It converts one form of energy to another. And this one, let's see if I can repeat that for you. This is really no strings. Okay, this is light controllably deforming a thin membrane here without touching it. We control it with polarization, et cetera. And so we have a lot of different materials that are far more advanced than this. This one moves a lot, so it's an old view graph where it says best material so far. What do you do with something like this? Well, you very simply take a laser beam. These are laser-powered nano actuators where every molecule is one of these. And you modulate the power and polarization. And if you've ever been to like a Pink Floyd laser light show, you use a laser scanner, you scan it over your membrane, voila, you have a very lightweight mirror system. And so since DARPA, I've got another grant from NASA headquarters from Office of Chief Technologist on this. It's part of the NASA Innovative Advanced Concepts program. and built a little test bed for controlling all of our beam parameters. And here's a small prototype where I'm scanning a laser beam over it and correcting the shape. We're using a sensor for feedback for the shape. So it's an active system. And our aerial densities are such that a 1 pound, well, let me back up. It's about 100 grams per square meter, and a Hubble-sized mirror would weigh approximately 1 pound. A JWST-sized mirror would weigh about 12 pounds. And you need a pound or two for the lasers and electronics if you build it really well. And so, great. Now that you have this ultra lightweight, inexpensive light diameter dish, or we're well on our way, what do you do with it? Well, you can use it for power generation. You can use it as a photovoltaic concentrator. You can collect heat and do thermoelectric conversion, Stirling, whatever. You can do a large collecting area for thermal regulation. You can make a materials reprocessing furnace for a Starship. You could do mass spectroscopy. Actually make a big mass spectrometer for recycling everything, right? Make an Icarus mass spectrometer after you vaporize stuff with it. You can certainly beam power. This is well known how to do this with microwaves and rectennas, and you can generate microwaves with over 90% efficiency. And so I'm going to skip some of these uses because I know I've got to be getting pretty short on time. 1 minute. Okay, great. You can distribute power to your other spacecraft. You can do laser comm because the cross-section of a beam and its angular divergence, the product is conserved quantity. Bigger beams diverge less, use it for communication. Solar sails, solar thermal propulsion, microwave drives, blah, blah, on and on. Multimodal propulsion for new missions. I'm going to skip through these. A spin-off. These are the Gumby bots, or Pokey bots. And so I've made a new 3D printer. We're about 90% done. And we have two different materials we're using. And they will move. And so this is a way to do very dense sampling with rovers. Rovers with wheels are terrible in gravity, right? If you want to explore asteroids, rover wheels depend on tangential friction, and so if gravity is very low, they just don't work well. So walkers work well if all you have to do is move your leg, shift your gravity, go back and forth. So working on that, and I think I'll end it with that. Here's a new technique for actually writing the molecular domain orientations using beams of light to control the cross-linking. This hasn't been done, but we'll do it in about a week from now. So it's pie in the sky stuff, but we're actually building it and doing it. With that, I'm just going to say this stuff looks like it's useful. All of these things have happened in these different areas since DARPA 2011. And of course, we had a student that did this nice picture. So I have to put this up thanks to Ariel Amato, now age 18. It's an old picture. Thank you very much.
So, Joe, the next conference is going to be in Maui, yeah? That's what I heard.
Any of you who want to come up the mountain on Maui, come see me. I'll take you up the mountain. You have to get there, but I'm happy to take you through our laboratories.
Was there any questions from the panel for Joe about his current work? Anybody in the audience want to ask Joe a few questions? Yeah, just over there.
Well, ask me in a year, but the real answer is it all depends on the support. And the idea is that you can correct a very high order. The proof's in the pudding. So ask me in a year as a function of size what the Zernike polynomials are. I'm hoping that we can correct several orders. So how well does it work now? You're asking what is the actual low and mid spatial frequency figure? And so what we're doing right now, we've been able to make things that look like we can achieve the diffraction limit. We are now closing the loop on a new control system. So ask me that maybe in 2 months. And right now what we're emphasizing is working on POSS materials that are atomic oxygen radiation resistant so that we can have, and I expect them to be completely different than what we've made. And so I haven't answered your question. How good is the figure? And so talk to me in a year.
Cool. Any more questions?
Yeah, Keith.
Can you see it? Oh, I thought you were giving me a 5-minute warning. I'll ignore him.
Really quickly, I actually really share your passion for open source, but I also know there's a big blind spot there and perhaps trepidation as to how do we monetize with open source. Do you have any prognostication or else any sense from your work with it on why it is or isn't a big issue going forward?
why open source is or is not a...
Why is open source a viable solution for monetized projects?
Well, there are a number of people who think it's a fine model for that. Because it's open source, and somebody said this earlier, was it you? It doesn't mean you can't make money on something. Now, so I think the answer is we generate a lot more knowledge. A lot of things come out of it. I don't know, Linux is open source, right? A lot of people have made a lot of money on that. So, I don't know. I mean, it's not the answer to everything. None of these things are, and none of these technologies are, and none of these business models are. It's a step. It's part of it.
And there's a lot of people involved with it. That's one thing I noticed from last year, 100-year Starship was on my track. It was human influences in, going to another star. And there was a huge number of open source advocates and makers and people who tinker with things. And they're just trying to find a way in. And they probably might do 100 projects and 99 won't make it, but that one may stick. So like the projects you're doing right now, you can see there must be an application there in
The
some
printed
way.
robots is going to be completely open source.
Yeah.
And that was a big thing last year. So many people came up and said, wow, I'm so excited. How can I get involved in this? And if we're looking at missions that cost trillions, multiple trillions, and we need the involvement of billions of people, I see no other way other than open source for doing this kind of thing.
Yeah, that's very cool. Thank you, Joe. Okay, so we'll go on to our next speaker now. Oh, unless there's any more questions for Joe. Yeah, we got another one. Okay, we got some time.
What kind of consumer applications can you see for this light bending technology?
Well, pumps for lab-on-chip that are optically controlled. There's a huge market for mirrors. I'm involved in a consortium where we're designing a 74-meter ground-based telescope, which should only cost $1 billion, which I know sounds like a lot, but it's probably a quarter of the cost per area compared to things like TMT and much better technology. There's a huge industry right now. I mean, at TMT, for example, they're probably going to spend a couple billion just on glass. Okay, they say the whole thing will cost $1 billion. I don't know, but there's a tremendous optics use for this. I've been looking at making ground-based things for adaptive optics with this. Most certainly, I've had some people approach me about using it for artificial prosthetics, and I've told them I don't think it's necessarily the right choice. There are a lot of possible uses, not just printing robots that can walk around.
Okay, we'll go to our next speaker now. It's David Weiss, VP of Engineering, Research and Design at Ike Industries Incorporated.
Good evening. Thank you. Good evening, everybody. I am an engineer and a foundryman, and I read however, I am a great reader of the material science journals that are out there. And about a dozen years ago, I suffered deep angst about what was going on in material science because there were so many good ideas and nobody could make so much as a coaster or a bottle cap out of the materials that were written up in the journals. And so there was very, very much a huge gap in there. Two things happened to me in my career. In 2010, I was invited by the American Foundry Society to give the keynote address. And I said, I'm going to have a little fun with it. And that address was making castings for the enterprise, okay? And talking about a lot of really advanced concepts and things that we weren't able to do, but things that seemed possible to me. So a year later, I presented at the first DARPA conference, and I expanded the talk a little bit and changed some things around. And I got great responses to both talks, and nobody told me I was insane. So that was a good reason to move forward and continue to do the work that we wanted to do. And of course, what intrigued me to begin with, that if you look at most materials, the theoretical strengths of materials are very, very high. In aluminum, which I'm kind of an expert in, the theoretical strength of aluminum is about 1 million pounds per square inch. That's the theoretical strength of that material based upon the atomic bonds in the material. In all materials, certainly in all metals, the actual strength that you get is at least an order of magnitude less than that. In aluminum, on a good day, we can make 70 or 80 80,000 PSI material, but certainly nowhere near 1 million pounds. The reason, of course, why people have trouble making bottle caps or coasters, let alone a panel for a Starship, is the fact that there's a lot of things that happen atomically. You have dislocations. Those dislocations move under force. They eventually cause material to fail. In aluminum and aluminum heat treating, what we do is we put other elements in there to precipitate, harden the material, and they become obstacles in that dislocation. But even beyond that, at the atomic level, there's all kinds of things that happen. And the reason that a lot of these materials don't grow into macro materials or real parts is the fact that the bigger they become, the more difficult they are to manufacture relatively defect-free. A couple presentations we talked about carbon nanotubes. There's a good reason that you can make a carbon nanotube a yard long, because it's extraordinarily difficult. Not impossible, but extraordinarily difficult to make a carbon nanotube that long that has any reasonable mechanical properties. So people get excited about things like graphene and carbon nanotubes relative to properties, but they suffer the same problems as metal. When you try to manufacture them into a real part, it becomes extraordinarily difficult to do. So we have imperfections on all kinds of different levels. And I chose to look at it this way, which says that there are things that are atomistically that are difficult to do, which may be possible to do in the future. But there's precision manufacturing. There are things we can do in the manufacturing operation that will significantly improve the materials we have. I read an interesting article about atomically precise manufacturing in metals, and the chemists do it every day, but not in metals. I mean, they make drugs which are very, very precise, other chemicals that are very precise. People are just starting to look at being able to do that in metals. The work that I'm doing is really on the smaller part of that pie, but that pie is not insignificant because you probably have about a 300% improvement in materials if you can solve some of the issues on that pie. Way back when the United States Air Force wanted to improve their planes, they said durability is related to initial flaw size and crack growth rate. So the first thing that you want to do is you want to minimize the flaw in the materials that you're manufacturing. And of course, this is a slide presented in the original conference in 2011. We put all kinds of bad things in metal when we manufacture. We put bad things in ceramics when we manufacture it. So we got to try to get rid of those type of things to significantly improve the strength. But we're getting there. We're making real progress. This is an aluminum silicon alloy. I don't want to bore people with microstructures too much, but on the left side as you're looking at it, you've got a fracture surface that is created by defects in the material. On the right side, you have a fracture surface that is fractured based upon the precipitates or the alloying elements that are actually put in the material. So we've looked since 2011 at being able to reduce those alloying elements, and in this particular alloy system, we reduce the silicon in the alloy and maintain the strength, but almost double the toughness of the material. So, and why was there so much silicon in to begin with? Because it was a custom. It was a Founderman's custom to put more silicon in to make parts more castable. And so you do that, and that's been true for 70 years, so you begin to question it, and you get some interesting results. This material is already in production with us. In general, the trends in material quality indexes continues to increase as our industry continues to improve. This is a slide from the original presentation where we talked about titanium. This is from the Journal of Materials, actually, so a scientific journal, if you will, suggesting a diamond fiber titanium metal matrix composite. We actually have something that's pretty close to that, which is an aluminum metallic glass composite. You have tensile strength in this material that exceeds 200 KSI. It was originally developed in 1987, but not really manufactured in bulk successfully until 2013 using high-pressure torsion. Okay? And the other interesting thing is if you pick the metallic glass right and put the right kind of carbides in, you'll be able to, you can inject hydrogen into the interstitials of those and create a material that is very radiation resistant as well. Yeah, I talked last time about nanocomposites. This is work that was done in a very, very small scale, and this is work that was done actually just 2 weeks ago. And if you look at this material in here and enlarged, and this is an alloy with 4% aluminum nanoparticles in it. So if you do a micro hardness in this field anywhere, you get a mechanical property of about 200,000 psi, okay, which is more than double the strength of the parent material. And this is some new work that we're doing with electrowetting. This was just in the literature, a completely new class of solid. It was looked at called Q glass, which is a combination of metallic glass and other structure, which is very interesting. And this is a process called ablation, where you rapidly cool the metal almost as soon as you pour it into the mold by ablating the mold away and getting very, very, very high solidification rates, which increases the mechanical properties. And this I had to put in this afternoon because I just got results. We're working with Oak Ridge on magnetic heat treating aluminum in a magnetic field, in a 9-torr magnetic field. And when we do that, the magnetism affects the solubility of the alloying elements, and we can heat treat aluminum in 45 minutes versus about 14 hours typically. So so that's brand new work. There's a great presentation today on 3D printing. 3D printing is going to be a very, very useful tool to make advanced materials as well, as soon as that technology goes forward. And so current metal trends support the Starship and its repair and maintenance from a structural standpoint. Serious design work will pull the rest of the technology into place. And as a project manager, I recognize I'm putting the cart well before the horse, because I don't have a design that I'm trying to make parts for yet. But the architects will come along and eventually surpass me. And there's more speculative technology out there that heaven knows what kind of material properties we're going to be able to get. Thank you.
Okay, are there any questions from the panel? Yeah, go for it, Joe.
That's very exciting stuff. And you mentioned materials with improved radiation resistance.
Yes.
Can you tell us a little bit about that and intuitively how they work?
Yeah, I was talking to somebody at lunch today, and it is possible under certain crystal structural arrangements that you can actually trap H2 in the molecule.
So it's sort of like the oxygen trapping in color centers.
Yeah, that's right. And one of the things we don't know is exactly how long it lasts. Will it percolate out over time? We're not sure of that, but we always, in non-ferrous materials, always said, well, hydrogen is a bad thing because it affects strength, okay? If you put it in and bury it essentially within a metallic glass, okay, which becomes your reinforcement phase, you're not going to give the negative effects of putting that hydrogen in the melt. And so you can get high enough levels of hydrogen, we think, that'll offer meaningful radiation protection in a lightweight structure.
So you bury it instead of getting the embrittlement?
Yes, yes, yeah.
I see. That's cool.
Is there any questions from the audience? Oh, right at the back.
Yes?
In the 60s and 70s, there was a lot of excitement, a lot of talk about ultra-pure whiskers of metal. Sort of like what the talk now is regarding nanotubes. Can you tell me how that compared, whatever happened to that stuff in the 60s, the great promise that they had for that ultra-pure whiskers of iron sort of thing, if you're familiar with that?
Yeah, I am. You know, there were two issues with it. One was a manufacturing problem, and the other a safety problem. Whiskers of anything, there was a lot of work done with whiskers and silicon carbide, where you developed amazing mechanical properties, but they were much, much worse for you than asbestos, okay? In the nano world, what we're trying to do is we're trying to deal with particles. Most of the particles are round. We try to pick those particles to be relatively benign. And of course, the verdict is out on the health and safety effects of nanoparticles, but a lot of people are working on it, and it does not seem to be the kind of problems that you have with those needles of ceramics and metals.
Any more questions? Oh, there's two just here. So we go for the last two at the front, just here. Yeah.
What is the role of the gravity in making the atomically ordered materials? The background of the question is that if the strong material can be fabricated on orbit where microgravity, then there's a very good chance for commercializing that kind of technology that would benefit someone on the Earth or some other public.
Well, if I understand the question right, you know, the role of gravity, you know, particularly in nanocomposites, in microcomposites, we worry about materials floating or sinking to the bottom of the melt. Typically, with the kind of particle loading that we're doing with nanoparticles, they're neutrally buoyant. They have such huge surface areas relative to their weight that they don't sink nor fall once that they are wetted in the material. The difficulty is getting them wetted into the material. That's the whole technology that we're trying to develop. And you know, once they're wetted in material, they're not going to move around. We've done melts of nanocomposites 5, 10, 15 times with no sinking or flotation of nanoparticles.
And last question, blue top.
You mentioned the radiation-resistant metal,
yes.
But I wasn't quite sure whether you were talking about your research on it, or if you know of any kind of research that's being done on it, or in the future.
Okay, what we have, there is some research going on, and I'm sorry I can't tell you which university it is because I learned about it actually at the Gordon Research Conference, which is typically unpublished work yet. But they have looked at putting hydrogen into carbides, specifically like carbides, as a potential radiation material. Our work before that had actually focused on putting high levels of hydrogen into an aluminum casting. And that work is under test right now as far as radiation resistance. The work continues. It's an active program at our place as well as a number of universities. But I think that radiation problem is solvable in lightweight structures without having to go to polymers or exotic shielding with water or magnetic fields. Yeah.
Would it have that dual product capability, so for like nuclear reactors and space vehicles?
Well, the problem with the materials that I'm working with are not high temperature materials, okay? So they're not going to be nuclear reactor type of materials. They'll be shielding / structural materials for flying in space.
Great. Thank you very much, David.
Thank you.
Okay, our last, but certainly not least, speaker today is Paul Gilster of Centauri Dreams. Big fan of his website. Check it out, centauridreams.com.
Thank you very much. I decided not to do any slides tonight. I'm asked to reflect on DARPA 2011 and what occurred. If you see slides being shown, maybe you had more wine at dinner than you intended to, because I won't do that. I can't think of a more congenial group than this. I've really enjoyed being with you all day today, learning from you and meeting a lot of my readers, which is really always a great treat to do. And I wanted to ask you a question, just out of my own curiosity. If it turned out that you learned tonight that there was a door prize and you could get a free flight into space, maybe on a Vostok or maybe on, I'm already getting hands up, or maybe, you know, through Virgin Galactic or something. How many of you would get on the ship to do that? I'm just curious. And as I suspected, it's hard for me to find an arm that's not up. I'm embarrassed to tell you that I would not do it. I'm actually a guy who likes this green and blue planet we live on, and I like the force of gravity. But I hope you all go, because I want to write about it. You see, what I do, this is my job. I write about what you do. And believe me, from my perspective, it's a distinct honor and privilege to do that. I have met so many people in this field who have been so helpful, who I respect so much. I bring my non-scientific skills to the issue of trying to make sense of what you all are doing, and lately what the organizations are doing. So for the last 9 years, I've been writing this Centauri Dreams site, trying to track all of that and keep up with what's going on. Not always an easy task. Now, before the DARPA solicitation in 2011, and actually if I went back to 2002 when I really first got involved in all this, I wasn't aware in 2002 of any private groups that were working on true interstellar issues, except Interstellar Propulsion Society, which had actually ended in the 1995 range. Mark Millis, as he mentioned, then went on to head up breakthrough propulsion physics for NASA. And so Tau Zero kind of emerged after that, and as Mark wanted to pursue these interests after he took early retirement. Now, between 2002 and really before DARPA, the organizations were sprouting like mushrooms. And we started talking to Project Icarus, that became Icarus Interstellar. We have the Institute for Interstellar Studies, and we can just go through this list now of all these groups, Starship Alliance and so on, that are coming out. And I'm not intentionally trying to miss anyone here. We've got Star Voyager and Space Gambit, all of these happening. Joe's Starship Alliance, I think I mentioned. All these happening really kind of around the same time that DARPA hit the news. So somehow the DARPA solicitation emerged at a time that was ripe for it. Suddenly the groups were coming out. That was important, but from my perspective, and when I was writing about, I was not yet seeing the public interest that would begin to emerge. And I think this is where the DARPA solicitation really began to make some changes in what was going on. If you look at what DARPA was after, and they were pretty clear about this, I'll just give you a couple of quotes. Sustainable model for persistent, long-term private sector investment. And they go on to speak about a myriad of disciplines needed, sustained investment over a century-long time horizon. And I think that's a fascinating idea, and I wanted to know about the inspiration for it. Those of you who are at the Orlando conference know that Dave Nalen, who was the tactical technology officer for DARPA and directly involved in this, had a great thing about Heinlein, and Time for the Stars was his favorite Heinlein juvenile. I reread those all the time, and I truly love them. And I can see why he picked that one. Because if you go back and reread Time for the Stars, what you understand is that Heinlein specifically talks about a DARPA-like situation. In other words, what he talks about in Time for the Stars is a group called the Long Range Foundation. It's not the Long Now Foundation of today, but the Long Range Foundation. And he describes it, Heinlein describes it through one of his characters, is for this group to get interested in your project, it had to be so horribly expensive that no one else would touch it, and the prospective results had to lie so far in the future that it could not be justified to taxpayers or shareholders. To make their eyes light up with enthusiasm, you had to suggest something that cost $1 billion or more and probably wouldn't show results for 10 generations, if ever. And I know, and I tried to ask Dave about this, and we didn't get a chance to get an answer, but I know that was his inspiration in thinking, let's create that group. Let's find a way with our 500K to create the sustainable effort that a long-term organization like this can make happen. And I think this is essential to the process. What did it do in terms of the public interest? And here again, this is my specialty because I'm trying to reach a lot of the general public with these issues when I write. I think that a great thing that DARPA 2011 did was to awaken people to the fact that there actually had been a long history of serious work on this topic. Star Trek was a great vision, but I think the people who watch it en masse tended to be people who understood it was pretty much fantasy in terms of what was going on there. I'm talking about your average viewer. The average viewer needed to be told that, no, wait a minute, people are talking about this. And not only are we talking about it right now, but look, we have been talking about this for quite some time. And if you go back in history, I mean, we can go back to the 1950s. Actually, you know, we could go back to the 1920s and early science fiction, and even a little bit before that. But in terms of actual science papers, in the 1950s, I mean, Les Shepard was writing in the early 1950s about antimatter propulsion. Eugen Zengram was writing about photon propulsion in the 50s. We had Robert Forward, laser sail ideas, George Marks, Clifford Singer with pellet propulsion, Greg Matloff, the great solar sail person of that era and still doing it, the late Eugene Maloff, Jeffrey Landis, who Forward mentioned as his successor, the one he wanted to succeed him. We had Alan Bond, Anthony Martin, we had Project Daedalus, British Interplanetary Society, continuing excellent work. Italian efforts, Giovanni Volpetti, Giancarlo Genta, Claudio Maccone. All of this was happening, you know, you get up to the 1990s and there's a lot of very sophisticated work going on. Mark didn't mention, but I want to mention meetings too, like Vision 21 that went on to study all of these matters from a very high level within NASA. The Breakthrough Propulsion Physics Conference itself was part of that. And Ed Belbruno did one that we haven't talked about called Robotic Interstellar Flight, Are We Ready? That was in the 1990s. Ed tells me that was one of his high points. He just loved doing that one, and they kicked all this around in New York City. So all of this was going on. And I think it's been very salutary that the DARPA solicitation has awakened people to that fact. And now when I speak to a lot of groups that are not as select as you in terms of your background and interest about this, what I get is that a surprise that, yes, we didn't know that it's going on. This is exciting. You mean real scientists think we might do it? And that's been a very good effect because now that affects funding. You see an interest. If we do get that exoplanet like the Earth, it's my personal view, that's going to be a real kickstart again for people to say, what do we do? When the Gliese 581 stuff came out, it turns out to be probably bogus now as far as habitability. I was getting calls from journalists all over the world on this question. I'm sorry, I'm not being audible. Excuse me. I was getting calls from journalists all over the world on the question of how do we get to this place? And so you start the conversation, well, you do understand how far it is. Well, no. Well, it's 20 light years. Well, yeah, but haven't we already gone to Neptune and stuff? You go through the conversation, but it was worth having. DARPA 2011 also reminded us that this is going to be multidisciplinary, and maybe we, in our scientific work, we weren't quite into that as much. It's going to be something that involves the entire species, because when we go, and we will, when we go, we won't just take scientists and engineers. We'll take philosophers, and we'll take poets, we'll take biologists, we'll take sociologists, the whole gamut. I mean, this is a species-wide effort that's got to be done. I talk about something that I call the Starship mythos all the time. Mythos is that Greek term that basically means a body of knowledge that teaches us how to live and inspires us in terms of how we deal with the really great questions of life and death and the things that we all face. And so a mythos gives us inspiration and tells us what our goals need to be. And I think what we're learning through this current activity, through DARPA, through this meeting, we're learning that as a culture, we have to remember what we knew long ago in ancient Athens and in the ancient Chinese dynasties. We knew that our works must not just reflect us, but they must surpass us. We must hand them along to our children to allow them to build upon them and discover their meaning and make them even better. So I say this, and I'm inspired by the DARPA 2011 project, and I'm inspired by all of you being here and by Icarus for having this conference. I say the problem of the Starship is a problem of science, but it is also a problem of philosophy as we discover how to live and what we want to do with ourselves. The problem of the Starship is a problem of engineering, but it is a problem of poetry as well, because we have to discover how to motivate our people to take these journeys. How do we go about doing this? And what I call the Starship mythos really means the place where there's an intersection between our dreams and our reality. It's that confrontation that changes both those things, both our dreams, both our reality, and helps us to draw upon our past for inspiration as we go forward. I think this mythos is what will reinvigorate us. I see it happening around me in the last few years. I have no doubt that at one point or another, whether in decades or in centuries, it will take us into the galaxy. Thank you very much.
Thank you, Paul. Was there any questions from the panel for Paul? Any questions from the panel?
Sure.
Go for it, Joe.
Yeah, so, of course, I only learn about these things from reading because there are people like you that write these things. And I went to VPP conference back when I was in NASA because Mark was doing these things. So I think there are just a lot of us that have been influenced by what you guys have done.
Well, you're very kind, thank you. But the main thing is we have to stretch outside our community, and I think we all know this in this room. We're all specialists. To some extent, we're all engineers, scientists, or very interested people. We have to reach the guy in the street to really fire him with the vision. Yeah.
Somebody said, you're going to this, and I said, well, it's not for everyone. Then I stopped and said, this really is for everyone. My question is, we have to bring the lawyers too, right?
Well, I'm not sure about the lawyers. I should have thrown in that qualification. I suppose we do, yes. I suppose we're going to have legal disputes that need to be adjudicated. So yes, by all means, by all means.
Any questions? Peter?
So that brings up. So of course, one way of broadly seeding is through the press and reaching a mass audience that we don't know who will take up and be interested.
Right.
But what about, and it's wonderful that there's the proliferation of societies that are largely self-selected, but what about the ways of self-replication and doubling? We have good models for the nuclear industry or the fossil fuel industry who have endowed chairs at universities that consistently turn out grad student after grad student in a tradition. Is anybody funding endowed chairs in universities to create a discipline.
One of our interests, one thing Tau Zero has been working at is trying to develop a structure to do just that, especially to get high-quality graduate student work involved with this. And we've been kicking this around quite a bit lately and setting up preliminary programs. And Mark, you might speak to what's going on.
Yeah, and while we've had some interest, some of the feedback we've gotten too from professors and things is that concern that they're giving a graduate student a topic for which there isn't a job opportunity there, that the work might still be too early. And I was debating whether or not to go into the details of the 2 test cases that we had for it at the Air Force Institute of Technology. But at this late at night, I worried that I might not recall those facts correctly. But it was interesting. We got one student to do one part. The other student, they felt that no, this is too far out, and it would not give him the kind of skills he would need to go on with other things. So that's one of the challenges that we're facing. What we haven't had trouble getting some discussions with various universities about it, and also the tactic that we're going to try is rather than us fund it ourselves, we are going to try and do a joint proposal where the professor in combination with the student and in combination with a couple of mentors or whatever from our expertise pool to get them started with the right reference list, that then going for educational grants instead of grants for propulsion or grants for this, because those seem to be easier to come about. But as such, so far we've only had one student, and he was funded by the Air Force.
Is there any more questions for Paul? There's one over here.
Yeah, hi. I don't mean to be a pessimist here, but I feel I need to ask this question because I'd like to hear the journalist's perspective, which is the DARPA conference put out a goal of sending a Starship to an interstellar body by 2100, but it's been over 40 years since we've been to the moon. Can we realistically make this happen?
Yeah, that's a great question, of course. My personal view on that is that that's not practical. What is practical is the creation of a 100-year effort that results in the technologies that take us much closer to a robotic mission. I think in terms of energy production, and if you look at the curves of advancing how much energy we can produce and the cost of it, 2 centuries to 3 centuries is a reasonable estimate for the first starships to go. I'm kind of pessimistic on that compared to a lot of our hosts here who are looking at within this century. And I could be totally wrong. But my personal view is that it is going to be an extremely difficult thing. I also think from my journalistic perspective that my job has to be to really try to lay out the problems to my reader. Because I want it to be clear that we don't want a backlash where the general public says, gee, it sounded so exciting, but now it looks like it's going to take a lot longer than we thought. Let's do something else. We're not a long-term thinking culture. So I think making it as clear what the problems are and the difficulties are is the best way to proceed. And then simply stress the fact that we're talking long-term, and we believe that as a culture, in the past we have proven we can do long-term. We should get back to that and stop being such a quarterly return society on things. Get it done in terms of not just ourselves, but our children, our grandchildren, our great-grandchildren. Build it for them. A lot of cathedral builders didn't see the building finished. They built foundations. And one of the cathedrals took 600 years. That was Cologne. You do something like that because you believe in what you're doing and because you're handing it on to your posterity.
I wanted to add too that the past
well, roughly half century of, not going back to the moon, that's not really a technological failure. That is a choice of our society and our decision makers. And even on our website, we say that, the progress is more limited by what our society chooses to do than how quickly we can figure out technology and science things. I mean, obviously here, we've got a lot of people who are doing work, kind of squeezing it beyond the edge of what their day job is, as opposed to, a well-funded effort. The other thing I wanted to add about, well, why even think about interstellar, is if you look at the history of technological developments, in particular when there are revolutionary points. For example, instead of further developing piston propeller aircraft, you go on to develop jet engines. Instead of better carbon paper, you develop photocopiers. When you change the mode of what you're doing, those happen with certain symptoms that are coming up, and those, at least, that cliche about those who don't read history are doomed to repeat it. Well, there's the other way of doing it. If you look at history and see the patterns, maybe you can ride them while they're happening. But anyway, with that as a preface, the interstellar challenge forces problems beyond just the extrapolation of what we already know how to do. If you're interested in that, go to the Moon and Mars communities and work on that. But if you really, and even if you're just talking closed loop life support too, if you talk interstellar, you have a completely different problem set that is much more challenging. And by that, it opens the way for more revolutionary solutions to come out, because you're not just trying to extend what you already know how to do, you're branching out into possibly completely different ways of getting it done. And then just from my own parochial part of that, that's why I have a pet interest on, instead of further advancing the technology, go back to the physics to find further advancements from which we can create a whole new era of technology from things that right now we're not even bothering to check for.
Can I add something to this? It's not at all clear to me that we're talking about humans in 100 years. It's not at all clear to me that the optimum thing to do is to send humans in their present form anyway. If we are interested, I'm not saying we shouldn't, right? But if we're interested in science, if we're interested in, say, remote sensing or exploring these worlds from distance or doing in situ stuff, it's not clear that 100 years and sending a human is the goal that we should all have. Right? Perhaps our goal is to, advance knowledge, like Mark was saying.
Well, the other thing too is that when it comes out, depending on what your motivation is, how you approach the interstellar flight situation is quite different. If, for example, survival of the human species is your motivation, then regardless of the time frame, the idea of designing closed-loop life supports, which would certainly be very valuable on Earth as well, is your thing. If your motivation is kind of like conquest, to be the first to do something, then you'll either want to be the first to launch something or the first to get to the destination, and that forces you into a different way of thinking. And if your motivation is just nudging things along a little bit differently, then you look at problems from a different way. So, and I notice here that a lot of the different audience actually has different motivations of what they're thinking of, and when the debate between human and robotic comes out as an example, and realize that we have different motivations. So when it comes to trying to pick where to focus on, it's not a matter of picking what's best, it's also first a matter of, well, best according to what motivation. And we often kind of gloss over that area.
Well, on that note, I better bring it to an end. We're running a little bit late. So thank you very much to the panel. I want to give them all a round of applause. And I just really want to echo what Paul said, that it's an absolute privilege to be part of the media, to be covering this, and it's even more of a privilege to actually be here physically. So thank you all for, thoroughly entertaining conversations, and it's been a really enlightening experience. So have a great night, and I shall see you tomorrow. But we got a announcement.
Just to confirm, we'll see you all 8:30 a.m. Will be coffee back in the room, and then 8:45 will be the intro for the next day. Dr. Minovich's keynote at 9. See you then.